Hello, ladies and gentlemen, and welcome back to another exciting episode of PASCO Live. This is a very special week because it's not just our regular Thursday presentation. Today is Friday, and it's not just Friday, it's Physics Friday. And you're probably wondering, like, what's it all about? It's all about great things that we do in physics and all the great demonstrations that you can do in your classroom. I'm JP, ladies and gentlemen, and of course this week the P stands for momentum. That's right, P stands for momentum. And if you're a physics teacher and you're watching, you understand exactly what I mean. Because today is all about physics. It's all about momentum. It's all about the great principles of physics that you'll be able to demonstrate whether you're doing hybrid learning or distance learning. In all of these cases, we're showing you ways today that you can demonstrate great things in your classroom, sell them to your students over the internet so that they can actually watch, participate, get involved, do analysis, and get back with you with their results so that you can actually do real teaching today. That's what it's all about. Today is Physics Friday, and we're doing all of this so that we can help you do great demonstrations at home. We know that you want to do demonstrations. We brought a great team together, so let me introduce you to the great team that you're going to be seeing today when we go through our demonstrations. Of course, I'm Dr. J.P. Keener. I'm the former director of STEM for the State Department of Education. I'll be hosting this event, but it's not just me. You're going to get to see great physics from wonderful physicists like Brett Sackett. You're also going to see today, as you've seen in many of our lives, Mr. Dan Burns. Joining us today on the set will also be Mr. J.J. Plank. And we have not seen yet, but coming in live today for the first time with PASCO Live, Miss Ann Hanks. You have not also seen, but will be seeing again, Mr. Jonathan Hanna. And of course, Boomer, the Boomer dog, is always with us here on the set. And a very special guest appearance, if you keep watching, from our own Mr. Paul A. Stokstad, who actually did put the P in PASCO, and we're happy to see Paul today. So we've got a great show for you today. We've got a tremendous amount going on today. We've got great demonstrations for you today, and we also have our FOMO promo. And what's the promo code for today? P stands for momentum. That's right, P stands for momentum, and if you reach out to our own Isaac Martin and let him know that, hey, P stands for momentum. He's got a great deal on all of the equipment that you're seeing today, all of the demonstrations that you're seeing today. Isaac is ready to put a deal together with you in our FOMO promo. Keyword P is for momentum. And there's something else that I want to introduce to you right now, but I'm going to talk to you a little bit more about, and it's our PASCO Academy. So we have this great opportunity. We're going to be showing you some great demonstrations, but we've heard a lot of people say, hey, JP, wouldn't you just like to do that for us in our schools every single week? And the answer is, yeah, I sure would. In fact, I would love to do that, and we're going to do that, and we have a program just like that, and it's called PASCO Academy. I'll tell you more about it as we get through our demos, but in this academy, if you want me or Ann or JJ or any of the great people that you see today doing these demonstrations in your classroom in a way that we can do and help your distance education, we're ready to do it. You can get more information if you go to www.pasco.com/PASCO-Academy, and you scroll down, you can enter your information to get more information on PASCO Academy. I'm going to tell you more about that soon. But what I really want to do right now is introduce you to our first and most excellent, most veteran member here at PASCO Laboratories, Miss Ann Hanks. Ann is responsible for many of the tools that you've been using in your classrooms for many, many years. She's been in the development, she's been in the training. Those of you that have been with PASCO for 55 years know Ann. I think she's been here for 55 years, and she will be working with us now. So, ladies and gentlemen, let me welcome to our set, and for your first demonstrations, Miss Ann Hanks.
Hello.
And I know you're very excited about doing these demonstrations. You've been practicing all week. You have some exciting stuff lined up for our physics folks?
Yes. And does veteran mean old?
No, veteran means you served in the military, Ann.
Of course, I never did that. Yeah.
Well, then it means old, Ann. What can I tell you?
So I want to begin by showing you a brand new kit that we have here at PASCO. It is the Smart Cart Demo Kit. And it comes with a beautiful full color manual for the teacher so that they can do all the demos that are included in this kit. There's this fan accessory, which I'm going to use in a second. And then the kit comes with a smart cart, a vector display, which Jonathan's going to be showing you in just a few minutes, the ballistic card accessory, a couple masses, the fan accessory, and this rod clamp, which allows you to make your smart cart into a force sensor that you can hang from a rod. There's also a secret thing in here today.
It's not going to be a secret after today, Ann.
Yeah, it's our new motor for the smart cart, and I'm going to show that to you as well. Currently, this is not really part of the kit, but we're going to add it, and so we left a spot for it in the kit. So, get rid of that. Thank you. One of the demonstrations in the kit is on the fan cart, and it's the old Roadrunner and Coyote thing where the Coyote gets on the skateboard and blows a fan into the sail, and he makes the cart go, which is surprising to physicists. I have here my smart fan, which is attached to my smart cart, and I got a little piece of paper on it here so that you can see which way the fan blows. You just go here and turn that on. So the fan blows that way, it pushes the air that way, and then Newton's third law, the air pushes back on the fan, which pushes the cart that way. So let me turn this off. What the Coyote does is he puts a sail up and then blows into the sail, and it's supposed to go that way. So let's see how that works out. In the demonstration kit, the files that come with it allow you to ask questions of your students. So in this case, it's asking which way is it going to move? Is it going to go the way the Coyote says? Is it going to go backwards, or is it going to stay still? And so let me turn it on. I can't see. Why is it not coming on? The thrust is set for the wrong thing. Set the thrust to 50. It just sits there. And then you can explain that the air is pushing on the cart that way, but it's also pushing on the cart this way when it pushes on the fan, and the two forces cancel each other out, so there's no net force. However, the Coyote was not completely mistaken. If we go on to the next one here, let me turn this around. So this has a slightly concave side to it, and it acts like a Pelton wheel on a water wheel, if you're familiar with what that is. And so now which way is it going to go? Is it going to go that way, or is it going to go backwards, or is it just going to stay still like it did before? Dan's saying this way. I'm getting kibitzed by the back here. And it does go that way. And so the Coyote was right in a way, because in his case, is getting the air to bounce off of the fan, the sail. And so there's a net force this way. And it actually does what it should do. And of course, that's why on a water wheel, you want a Pelton wheel, which pushes the water backwards, and you get twice the impulse. Okay, so let's be done with that one. And here is our new Smart Cart motor. And it's plugs into the accessory port just like our other accessories for the Smart Cart. And it has its own battery so that it powers itself, but it's guided by the Smart Cart. So we can control the motor through our software. Let me switch programs here. You know, I'm going to have to disconnect from that other Smart Cart. There we go. Now I'll just connect to this cart. So now I have control of this cart. Get this down out of the way here. This is not going to work here. I really need to push this forward here. There we go. So in our program now, in both Capstone and in SparkView, we have Blockly programming. So here I have a program that I've written to make my my motorized cart go. And I have programmed into it the equation x equals v naught t. And in this case, v naught is 0.1 meters per second. Why squared? Okay, we're going to edit on the fly here. Wrong units. That's weird. So the instructions, when I push record, are going to go to the cart and tell it to run the motor at a certain speed, at 0.1 meters per second. I also have a graph here of the position versus time. And so it's trying to go at a constant velocity, and it is managing to do that, as you see. And the resulting graph is a straight line of position versus time. And this is really interesting to show students what it means, what the equation means, because that velocity is the slope of that line. If I go to the next page here, there is, again, my mistaken units. And I'm going to change the velocity in the program to 0.15, and now we can see what happens this time. And you can see that the slope is now larger because the speed is larger, but it's still a straight line. It's not straight right at the beginning because in the program, the cart is saying, okay, I've got to go 0.15 meters per second. Am I doing that? No. Then it compensates. So it's looping through and compensating so that it makes it go at that constant velocity. So now, of course, I'd like to see what happens when there's an acceleration. So let's see here. This is a similar program, but this time x is equal to 1/2 at squared, and there's no initial velocity, but it's going to accelerate at 0.15 meters per second squared. Let's let it rip here. And you see that the position versus time graph now is curved in a parabola because it does go as t squared. And if I change that acceleration to, let's just say, 0.1, then you see what happens to the graph. It's still a curve, but it's a lower curve because it's not accelerating as much. So one final thing I want to do with this is actually have initial velocity as well. And so in this case, I'm going to start it right here because I noticed that my acceleration is negative. So I have x is v naught t plus 1/2 at squared. And so there's an initial velocity and there's an acceleration. The initial velocity is 0.15 meters per second, and the acceleration is a negative 0.05 meters per second squared. So what's it going to do? What will be the motion of the cart? Will it be a straight line like it was before? I don't know if you can be heard on camera. Yeah, my student just said it's going to be a circle. So is it going to be a curve like it was when it was accelerating? Let's watch. It's having a little trouble finding it there. Oh. So as you can see, instead of curving up, since the acceleration is negative, it curves down, and it actually backs up. First it's slowing the cart down, and then it speeds it back up and it goes the other direction. It had a little trouble finding its velocity, but that's can be fixed by changing my program and increasing the data rate that we're using. And there's lots of ways to massage that data. Okay. This also will run on the floor. So if you want, you can just run it on the desk. And I'm seeing it here. This program is just a randomized position. It's telling the cart to go to a certain position, but it's a random position. And so we use the random number generator in Blockly to say where you want it to go to, and then it goes to that position. And you can see on the graph the position versus time. The square curve on there is where it's being commanded to go to, and then the curved part is where the cart is reacting to go to that spot. There's a dozen things you can do with this. One of the first things I did with it was I just took a force sensor, and a wireless force sensor, and I palmed it in my hand so no one could see that I had it. And then I pretended that I could make the cart go just by asking it to come, like a dog. And I'd push on the force sensor behind my back, and it would come towards me. And then I'd say, "No, stop," and I'd make it stop. All right, so Jonathan, are you ready? Come on.
So Anne, I want to thank you for this. And really one of the very exciting things about what we see here is that Anne is demonstrating a product that you haven't even seen yet. In fact, this product is so new and so hot, and I don't think it's on the website yet, is it?
Nope.
It's not even on the website yet. And so this opportunity for you to see something that's coming out fresh ties into that great promo that we're offering. If you want to get a great price on this before it's even on the website, reach out to Isaac Martin and say, "Hey, P stands for momentum. P stands for momentum. I really like that cart. I'd really like that cart motor. I think that's going to add a lot." And you did notice that they integrated in fully the computational thinking component that brings the Blockly in, that brings in the science, and ties the two together. So remember that. And also remember, Jonathan, you can come on in and set up. Remember, kids, if you want these demonstrations done for your students, if you want us to do it for you, because we've got the equipment, we've got the laboratory, and we've got the expertise, we can do it for you, and it's called PASCO Academy. I'll be telling you more about PASCO Academy, but I know you want to see another exciting demonstration. Welcome, ladies and gentlemen, Mr. Jonathan Hanna.
Sorry, I got my mask caught on my glasses there. All right, so hello everybody, I am Jonathan, and what I'm going to demonstrate to you today is another part of the demo kit that we have, which is the vector display. And this is my absolute favorite one from the demo kit. I love this thing. When the smart card first came out, this is one of the first things I asked for. I said, we got to have something that we can visualize the sensors that are on this thing. Before I came to PASCO, I was a physics teacher. I was teaching conceptual physics to 9th graders. And one of the toughest concepts for them was trying to understand how many variables have direction associated with them. So with the smart cart, of course, we can measure velocity, we can measure acceleration, and we can also measure force with a force sensor on here. And we can control that with our software. And all I'm going to be doing here is just using the software to change from one measurement to another measurement. So right now we have that set for velocity. Now velocity is probably the easiest one to understand out of all the vectors, because velocity, the direction of velocity is just the direction that the object is moving. So if I move it backwards, you can see that it points in that direction. Move it forward, moves in the opposite direction. So that one's pretty easy to grasp. That's a good one to start off with. Another one that's not too tricky to grasp is force. So let me go ahead and change that to force. Now the smart card has a force sensor right here, and there's many different accessories that we can use with the smart cart force sensor. In this case, I put a spring bumper on there because it does a really good job of visualizing the force I place on the cart. So if I push on the spring that way, you can see the spring is compressing, and you can see that the direction of the force on the cart is pointed in the same direction that I'm pushing. If I pull, we can see that it goes in the opposite direction.
I see why you like this.
Oh, of course. It's wonderful. Now, the toughest one to understand, at least for my students, and actually for myself too, actually, when I was playing around with this week, I had to remind myself about some acceleration concepts. But yeah, the direction of acceleration is a little trickier because it's not acceleration, in physics. The way that we measure in physics isn't, with our common experience in life. It's a new concept for students. So let me switch it to acceleration. Okay, so now in this case, I'm just going to make the card speed up by tilting the track. And I can't see the vector display right now, but I'm hoping that it actually is pointing in that direction.
Yes.
Okay, excellent. Woo. Good thing, physics works. All right. Now let's try to slow it down. So to make the card slow down, I'm going to use this friction block. And I'm going to use the plunger on the cart to launch the cart. So when the cart was speeding up down the track, we saw the acceleration pointing in that direction. So when the cart slows down, what will happen in this case? I'm hoping that it pointed in that direction. OK, good. Yeah, so when the cart was slowing down, the acceleration was pointing in the opposite direction that it was moving. And just to confirm, just to make sure that, velocity is still pointing in that direction, let's go ahead and switch it. Okay, so we're back to velocity, and velocity is pointing that way. So when the cart's slowing down, the velocity is in that direction, acceleration is in the opposite direction. When it's speeding up, velocity is pointing in that direction, and we also saw previously that acceleration was also pointing in that direction. So let's take this another step further. What I'm going to do now is I'm going to incline the track. So let's see, where's my, oh, there it is. We're going to use this accessory. Oh, thank you. Yeah, I guess I don't need an end stop up there anymore, do I?
Well, I don't know.
Okay. All right, there we go. That should be a pretty good incline. And let's see. So let me put the spring bumper back on there so we can make this thing bounce back and forth. So let's start again with velocity in this case. Okay, we got velocity set up. So what I'm going to do here is I'm going to have the cart go up and just come back again and bounce a few times. So let's take a look at the direction of velocity. Whoa, that's too much. Okay, maybe I probably shouldn't be doing it that much of an angle. Let's bring that down a little bit. Okay, this might be a little bit better. Let's try that. That's still too much. Wow. Okay, let's try it one more time. How about at this?
That's where inclining with a book helps.
Yes, exactly. Actually, I think I was testing out with a book when I was doing this. Okay. So as we should be able to see, the velocity is that direction when it's going up. When it's going down, it's going in the opposite direction. Now let's look at how the cart is moving. So as it goes up, is it speeding up or is it slowing down?
Slowing down.
Thank you.
Slowing down.
Slowing down, okay. And then as it's going down, it's speeding up. Okay, excellent. So let's think about that for a moment. So as it's going up and slowing down, which way should the acceleration be pointed? And as it's going down and speeding up, which way should the acceleration be pointed? So let's take a look. Stop. Okay, now let's take a look at the acceleration. So what do we predict? What do we think? As it's going up, which way should the acceleration be? We know velocity is this way, right? So
Acceleration is in the opposite direction.
Opposite direction, so it should be down that way. Okay, all right, well, let's see. Were we right?
Yes.
Yes, okay, good. All right, it works. Okay, so now going down. It's going to be speeding up going down. You know, velocity is in this direction, so which way should acceleration be?
Speeding up, acceleration's in the same direction.
Same direction. So let's see. And indeed, it is. So acceleration is always pointing in that direction in this case.
Yay, Jonathan!
Woohoo! Yeah. All right, got one more for you.
But wait, there's more.
There's more. I mean, there's so many things you can do with this, but we don't have enough time for that. This is where I wanted my track to be inclined a little bit more. And this is actually where I do need that end stop. So where did the end stop go?
Sorry.
That's okay. All right, thank you very much. So now let's try this with a spring. And I'm going to change my accessory on the force sensor to a hook so we can actually measure the force. And I'm hoping, I'm looking at the right camera, right? Is it that one? Okay, good. There's no cameras? Okay. See, I usually do the writing. I'm not usually in front of the camera, so this is a whole new thing to me. Whole new genre. Okay. And you do not see you're not looking at the cart that way. I should not be doing it that direction, should I?
Here.
Let me do it the other way.
Why don't you just flip the whole thing
Flip the
around? Whole track.
flip the whole track around? Okay, I guess we could do that. That would be be much more simple, wouldn't it? Okay. It's a good thing we got a whole team in here to help us out.
I'm here for you, Jonathan.
Thank you, JP.
All you got to do is just call out, and I'm right here for you.
All right, appreciate that, JP.
I know how difficult this audience can be.
All right. Okay. So let's start with velocity. Now this is very similar to what we were dealing with before, only we've added a new force because previously we just had a force going in that direction, which was due to gravity. But now we have a new force due to this spring. And velocity should be pretty obvious. Yeah, so we should be seeing up, down, same direction it's moving. Okay. Now, let's take a look at the direction of acceleration. So again, let's just focus on the cart moving for a second. So let's see. What type of movement do we have going on here now? We got speeding up and slowing down going on. So what about in this case, as it's going down the track? Which way should the acceleration be pointed? As it's going up the track, which way should the acceleration be pointed? This one's a little bit trickier. Let's take a look at the acceleration now. Okay, so obviously not moving, the acceleration is 0. Now as I bring it down, so what do we see? And make sure I can see it too. Where does it appear that the acceleration is 0 in this case? Is that it's not 0 at the top of the track, it's not 0 at the bottom of the track. 0 right around here, it looks like. So that's interesting. So why is that occurring? So as we get to this spot right here where the acceleration is 0, the cart is slowing down at this point, right? So we have the acceleration pointed in the opposite direction there. As it keeps on going down here, it's speeding up, and then once it gets down to this point right here, it's starting to slow down again. So since it's moving in that direction, the acceleration is pointed in the opposite direction. Now let's just take a look at the last one, which is force. Okay. So we currently do see a force on here due to the spring. I'm going to pull it down just a little bit more. Let's look at what happens to the force in this case. So we see that the force is actually decreasing as the spring is coming back to its natural position. But of course, that's only the force that is on the cart right here on the force sensor. that's not all the forces that are on the cart. We're not really considering the net force on the cart. So this doesn't really do a good job of explaining why the acceleration is 0 at this point and then changing as it's going up and down. So in order to understand that a little bit better, we need to actually find the net force on the cart. So we can actually see the net force by zeroing the sensor at this point. So I'm going to go ahead and zero the force sensor.
So just to let you know,
Yeah.
if you had read the teacher's manual for the demo kit,
Yep, which I did not, sorry.
he only reads his own stuff.
Yes, exactly.
It says to mark equilibrium with this foot.
Excellent. I love it.
Thank you, Ann. Thank you, Ann.
Okay, so let me go ahead and zero the force sensor.
And that's why she is the queen of physics.
Exactly. Okay, so we got the force sensor zeroed. Now let's take a look here. Does that look very similar to what we saw earlier with the acceleration? I know it's not the same magnitude, but do we see the same direction? Oops. And we're live, aren't we, right? This is why this is the first time you've seen me, and this probably will be the last time you see me. Okay, but you get the picture here. The force, the net force and the acceleration both share the same direction. And that is the vector display for you. What do we have next?
Thank you, Jonathan, and thank you guys at home, and for all of you who keep asking in, and especially Sesha, who joins us in every one of our sessions from Florida Polytech, who says, I love your physics demonstrations. Well, we're providing a whole bunch for you. I hope you pass this off to your faculty and they get something out of this. The neat thing about the vector display, somebody had asked, like, how do I know if it's force or acceleration? Can I see that cart real quick, Jonathan? Can you hand that here? Because maybe folks didn't see it, and whoever's coming in can set up for our next one. But you do notice on the front, it does tell you actually, and you might have seen that changing, but it tells me force, acceleration, velocity. So the lights on the front actually tell me what it is that I'm measuring when you turn it on, and then you're able to see that. So if you would like Jonathan to do this demonstration, probably after he's rehearsed it a few more times in your classroom, he will, he can, and he'd do it for you through PASCO Academy. All you have to do is check out PASCO Academy and see how we could do these demonstrations in your classroom should you not have this equipment. Who's up?
Let's do an intermission real quick. We'll do it with Paul.
Oh, okay. We've got a special opportunity with Paul. And let's go to that now.
Good morning. We have with us today Paul Alan Stokstad of PASCO Scientific. Thanks for joining us, Paul.
You gave away my favorite question. What does the A stand for?
What does the A stand for?
It does stand for Alan.
Oh,
But
great.
so it was my mother gave me the name Paul Alan Stokstad, so it's that plus CO on it
Okay. That's what the PASCO stands for?
is Paul Alan Stokstad Company.
Oh, great.
Right.
So how long have you worked for PASCO?
I actually haven't worked for PASCO at all. It's just been fun. PASCO is now, I think, 57 years old. Started when I was a freshman in college. So,
Awesome. What do you think your second job is going to be?
ooh, I have it right now, actually, and that is being able to go and talk to people and give unwelcome advice and see the amazing job that they're doing. So
Okay.
I'm a cheerleader, I'd say.
Awesome, awesome. So I've heard that there's a PASCO product that is called the pantyhose meter, and I've looked on the website and I can't find the pantyhose meter. Can you explain that?
Uh-huh. Well, in the 1970s, there was sort of a crisis in apparel. Synthetic fabrics were taking more and more of the market, but they had a problem. They would get static charge on them, especially in the winter dry day. And so that if a lady put on a skirt of a synthetic and maybe a synthetic blouse, she'd move around a bit, the fabrics would rub against each other, and all of a sudden it was clinging.
Yep.
And
I think I remember these commercials.
My new pantsuit has an old problem. Static cling. But watch. This is new Static Guard.
This was a real problem.
A global crisis.
A global crisis, and Kaiser Roth, a big fabric company, went to their local physics department and said, how do you measure static charge? And they said, well, we have this PASCO electrometer over here that we use. And we had the electrometer connected to a Faraday ice pail, and you'd rub onto the fabric, stick it in the ice pail, and get a measurement. So we went back, took a look at it, and they said, build us an instrument that'll make the measurement. So we went back, and in about 3 weeks, we actually had put together something that had an electrometer, had a Faraday ice pail, and then had a motor to run against the cloth.
Okay.
And we sold we built 8 and we sold 4. And unfortunately at that time, someone came up with a good solution that eliminated the whole problem. And we were left with 2 units, which are somewhere around here. But that became known as the pantyhose meter.
Okay, awesome. So I hear down in Columbia, there is a physics lab equipment cartel. And this cartel knocked on PASCO's door one day with a suitcase full of cash, looking to buy physics equipment. Is this true?
This is true. And we knew nothing about it, but this lovely woman named Elsa Mora came and said, I'd like to get some physics equipment. I have a copy of your catalog. I'm from Columbia, and we'd like to buy some. Why not? So we went around and she picked out what she wanted, and we said, do you want us to ship this to you? She says, no, I have my suitcase. Okay, she opens up the suitcase, puts the equipment in, takes out an envelope of cash, cold hard cash, and picked up her equipment and went on. And Elsa and her husband Angel are still very good friends of ours.
Awesome.
But there was no cartel.
Okay, so they're not running the physics lab
They're
equipment
not running
cartel in
physics
Columbia.
equipment.
Okay, I'm glad we cleared that up. So my fashion sense today is inspired by you.
Oh dear.
And so I'm wondering, where do you get your fashion sense from?
No longer from Brooks Brothers. They disappeared yesterday. I have no sense on it. I'll tell you, if it's a matter of getting a suit, the first day I go to the mall or whatever it is and end up in the bookstore and never get out until 9 o'clock.
Right.
Second day I decided it's probably black or blue. Third day you go and you buy it and you leave and you're glad the process is over. I'm not a fashionista.
Okay.
Well, not at all.
But do you think everyone at PASCO should be wearing bow ties?
That's a loaded question. At a certain time, i.e. at a American Association of Physics Teachers convention, all PASCO people should have a red bow tie.
Yes, I agree. I brought it back. So we have a PASCO guitar here. Did you want to jam for us?
No ability, but this is a most amazing guitar. But a gentleman named Mr. Brett Sackett surprised me one day with this, and you look at it, you don't realize what it is. Your brain hasn't put all the parts together. But shortly thereafter, I did realize it, and it's probably the nicest thing I've ever received. It's a tribute to all the folks at PASCO who keep making better stuff.
Absolutely.
Now, are you going to jam for us?
Probably not today because I don't have an amplifier big enough.
Ah.
So, when you were young, you would enter science fairs.
I entered science fairs for the prizes, I hate to admit.
Kind of as a hobby.
It was a hobby. I just like building things.
I think we know that. So, no football?
No. We had a trampoline in our high school, and when I got on it, the coach would say, "No, Stokstad, no."
All right. So you won a science fair where you would enter the Millikan oil drop apparatus.
Right.
And you won.
Correct. Well, they actually had 6 first places. Everybody in that group was a first place.
Oh, okay. All right. Did you have to bribe the judges?
No. But that's not a bad idea.
And so that's effectively how PASCO got started, was the Millikan oil drop apparatus.
The Millikan had built that as a science project, and a teacher, or who was one of the judges, said, "Young man, I'll pay you to build one of those for me," which I never did in high school. But I got to college, and I realized every other kid there was smarter than I was. They understood physics, and I was a total klutz. And so built it, and the most amazing thing after building 20 of them and putting an ad in the journal was various schools had purchased 17 units. If you took the value back to what it was then, it would have been worth about $2,000. and they were willing to take a trust on a person they had never met, a company they had never heard of, and a product they had never seen.
That's great. And we still sell the milk and oil.
We still sell it.
A more modern version of it.
It's been improved. We're now up to LED lights. So we're moving along.
Excellent. So one last question. If you could buy your wife an anniversary present from the PASCO catalog, what would you buy her? Sky's the limit.
If it wasn't the PASCO catalog, it would have been the Dyson vacuum cleaner, because I marvel at that. But what?
There's so many to choose from.
Exactly.
How about a smart card?
So a smart card she would enjoy. In fact, actually, she'd even enjoy the very first one that was aluminum. The rest of the electronics you can put aside.
Okay, yes. The aluminum PASCO card, still a great card.
So, do I get to ask a question?
Go right ahead.
Mr. Sackett, you've been here how many years?
I've been here for a little over 20 years.
20 years. What is it about PASCO? I know what put me here. I'm here. But what was it about PASCO that encouraged you to sign on with this group of great folks, but sometimes a little bit wacky?
So I remember my interview process. I was given some equipment to take home and figure out. And I had not used any sensor technology where I went to college. And I was immediately I enjoyed using the sensors and the interface, and I had a cart and track, and they wanted me to come back and show how it all worked. And I was blown away at collecting the data, at seeing the graphs, doing the analysis in the software, and I said, wow, this is amazing. And then when I started and we did the sensor-based diffraction apparatus, that blew my mind. Because when I was a physics TA, of course I've done all of these experiments, but we did not use the sensor technology, and it was amazing seeing the data collected in real time and just beautiful graphs being made. And so it was that, and then getting out and talking to physics teachers and other science educators, and it really just became my career to learn more about science education and the equipment needs of schools and physics labs everywhere.
Well, I'm very glad you put in with us.
I've enjoyed it.
And a lot of kids have learned a lot of good physics from the work you do, so thank you.
Thank you, Paul. Thanks for joining us for our PASCO Day of Physics. We're going to have demonstrations and do some cool physics things, so thanks everyone.
Nice to meet you.
Are we going to transition soon?
And we're back, and I hope you enjoyed that very awesome interview by Paul Stokstad, who put the PAS in PASCO, and you can see how excited he is about our products and why it's so exciting to work with somebody like Paul, and why it's so awesome to come to work every day and work with fine folks like you see here today. So awesome, Paul. Thank you for that, and thank you for everybody who's really putting out some really great stuff. So what we're doing now is bringing in somebody who you've seen before. You've seen him on probably every video that's on our video channel, is JJ Plank, who's going to be shooting things in the classroom. And typically that wouldn't be politically correct, but today it actually is. And he can do that while wearing safety glasses, and we're going to be doing some projectiles. So JJ, what do you got?
Okay, JP, thank you. Thank you. So what I wanted to do today is show you some functionality in Capstone while also doing a little bit of a demo. Capstone software now has the ability to include Blockly coding as part of it. And so what we see a lot are pushes and encouragement to include more computational thought in the way we teach physics. And Blockly is a perfect tool for that. And the way that I like to use it in uses, the number and styles of uses are growing every day, but one of the ways that I really like to use it is with projectiles. More specifically, Capstone will show you data that you can produce using Blockly code, and what I want to do is produce data that models the path of a projectile. So a lot of teachers, and I've done this as well myself, a practicum that we have our students do sometimes is let's say we have a projectile launcher. We know the starting height, the starting speed, the starting angle of the projectile. Let's figure out what the path of it is. And so we'll set up ring stands with rings set vertically. And we want the projectile, we want to put them in a position so the projectile goes through all of them, right? And so it can be a real meticulous process doing that. You know, you got to figure out the position of each one of them. And it can be very useful and very good for students to do that. They understand the math. But another way that we can do that is just how I described. We can use coding to help tell us the exact position of the projectile through its path, okay? And what I've done here, and I'm going to go ahead and bring up my code, is in Blockly within Capstone, I've written a block of code, and let me zoom out just to show you that it's nothing super massive. So it's really basically one big loop. These purple blocks at the top are mostly variables that I'm defining. But if we zoom in here a little bit, and these yellow blocks or brownish green colored blocks are outputs. So the code is going to output data that we're going to use to plot in a display, which is super convenient because let's say we were to do something like this in another coding language, we would have to get the raw data out, maybe text as a tab delimited format, then we'd have to find some way to plot it. And this helps streamline that process by doing it all within Capstone software. And so what our code is doing is it's focusing on the forces that are acting on the projectile, right, once it's in flight. So we're going to ignore everything that happens when the projectile is launched, but we want this code to tell us exactly where the projectile is going to be after it gets launched at different times, right? And so one thing we can do is focus on just the forces that are acting on it. And once the projectile is in the air, the only forces acting on it are a gravitational force in the vertical direction, right? As well as a drag force that acts on it depending on the direction it's traveling, okay? And so that's exactly what I've done here in my code is I've set these two drag force equations into my code. And this is our standard drag force equation that looks something like this. Drag force is equal to this drag coefficient times the cross-sectional area of the projectile, right? The density of the fluid it's traveling through, in this case it's air, and then the flow, right? The velocity, basically, the speed of the projectile. So relative to the fluid, but in this case, it's just the speed of the projectile. And then you divide that by 2. And in my code here, that's what I have. Here's my divide by 2. Here's my drag coefficient times the cross-sectional area times the air density times that velocity in the x direction squared. And so since forces, we can break them into their components, we can treat the x and y independently and then combine them at the end if we need to. And that's what I've done here. So as the projectile is traveling at a non-horizontal or non-vertical direction, we consider both drag forces in the vertical and the horizontal simultaneously. And so we've got a drag x, a drag y, right? And then we've got a force x and a force y. Because drag is not the only force that's acting on the projectile, we have to consider gravity in the vertical. But you'll notice here my force x, which represents the forces acting on the projectile in the x direction, the horizontal direction, is just that drag force, okay? And the vertical forces are the drag force plus the gravitational force, which is what I've got here. mg, m times g, plus that drag force. We just add them, right? We sum the forces, okay? Then, to figure out how those forces are changing, as well as the position, as well as the velocity of the projectile, we can address that using the projectile's momentum, right? And so that's what we do right here. The projectile starts with some momentum, and that momentum is affected by impulses, right? And those impulses are a result of forces. So you apply a force over some time, you get an impulse that changes the momentum of the projectile, and that's exactly what we're doing here. We're taking that momentum and we're changing it based on these impulses in the x and the y direction. Okay, then from momentum, right? Momentum is just mass times speed, right? Mass times velocity. We can take that momentum and figure out what the position is based on it. We take the momentum in the x direction, divide by its mass, multiply by some time step, right? And then add that to its existing, the position before. So at every small amount of time that we're going to tell this code to use, we're recalculating the momentum, the position, and then right below it here, we're also calculating the velocity, but we're doing that all using just the forces acting on it. Okay, there's no range equation. There's no complicated sine theta in here. Well, there is at the top, but that's only for to define the initial angle and the initial speeds or velocity of the projectile. But what this code will do is it will model the path of this projectile. And I'm gonna go up to the top here. Before it can tell us exactly what the path is, we have to tell the code a couple of things, a couple of coefficient values that we need to add in there. One is the drag coefficient, right? So if we were using something that had a lot of air drag, that drag coefficient would be higher. In this case, we're using a small cylindrical projectile that has a really small drag coefficient. And for the purpose of this, I'm just going to leave it 0. We need to know the initial speed, the initial angle, and the initial position of the projectile, right? And then there's some other variables in here, or excuse me, coefficients in here that we're going to set and keep set, right? G, acceleration due to gravity, the time step in between every time this code recalculates position, velocity, momentum, all that stuff, right? The time that we want to start at, the air density, right? And then the cross-sectional area of our projectile. So let me grab a projectile, and I'll get back down here. So it's just a small cylindrical plastic projectile, right? It's got a mass of about 9.6 grams, okay? So we know what our mass is, and I'll enter that value. It's already entered incorrectly. Okay, whoops. We'll let that one go. I've got more. Okay, so then the other things we need to enter in is the initial starting position or the starting height of the projectile. And we can look on the side of our projectile launcher on the barrel here. There's a little arrow that tells us where to measure the starting position from for our projectile as it leaves the barrel. And in this case, it just happens to be exactly 1 meter, which is kind of nice. All right, so I'll set my Y position, which is my initial Y position. I'll just make it 1 meter. And then we'll leave the X position 0. The initial angle, there's also a scale here, 45 degrees. It's already set to 45 degrees. And then the initial speed. So we need to know the initial speed of the projectile as it leaves the barrel here, the muzzle velocity basically. And so what I'm going to do is I'm going to use this wireless smart gate that's attached to the front here to measure that. So I'm going to collapse that code for a second. I'm going to go ahead and make a new page. Whoops. Double click for a digits display, and then I'm going to put my speed between gates as it's measured from that smart gate. And so let's go ahead and measure this. I'll load this. Let's do, the projectile launcher has different settings for barrel velocity, or speed I should say. And I'm just going to press it in so it clicks twice. There's 3 clicks. So you've got 3 values that you can start from. I'm going to start recording. Nothing's going to show up until the projectile comes through. I don't want it to fly over and hit Ann. Oh, I guess it could. So you ready, Ann? There you go. And so I'll go ahead and stop this. And so the muzzle speed of our projectile is 4.8 meters per second. So I'm going to go back to my code. I'm going to go ahead and delete that run. We know it's 4.87. And I'm going to go in here and I'm going to change this to 4.87. Okay. Like I said, I'm going to leave the drag coefficient at 0. So we've got everything set. So now what I want to do is I'm going to go back to this page. And this page shows a table as well as a graph display with our position data that's calculated through that code, through that Blockly code. It's the position of the projectile based on those initial conditions. So I'll go ahead and click record, and you'll see here that data gets plotted, and this data represents the path of that projectile. So launching at a 45-degree angle, launching at a muzzle speed of 4.8 meters per second, drag coefficient of 0, cross-sectional area that we set, a mass that we set, I measured it using that balance right over there. Now we have the XY position of that projectile as it travels through the air. So now all we need to do, let's say we're using those ring stands, now all we need to do is find out on our graph here where to set our rings. So the projectile goes through it, right? And so I don't have ring stands, but I do have this guy. And what this is, it's just a little 4x4 piece of sheet metal hanging from a pendulum clamp. And then this is just a pendulum bob, right? And so I have tape measure on the floor. And what I'm going to do is I'm going to measure the height of this. And I want to figure out where in front of this projectile launcher can I set this where that projectile will hit that thing square in the middle, right? And so all I want to do, or excuse me, I shouldn't say all I want to do. First thing is measure the height, okay? And I'm going to measure it from that post right there. And it just so happens to be 1 meter from the floor to the center of this, right?
That's very convenient, JJ. Very convenient.
Very convenient. That's right, yeah. We could change it.
We could.
I'd be, yeah. So it's not quite exactly 1 meter. It's actually 0.99 meters. Okay. And so what I want to do is I want to set this position, you know, the range and height of this sheet metal so the projectile will strike it. If I know the height is set at 1 meters, I can go over here to my graph, take this coordinates tool, and then I can scan through the data and find where my Y component, see my X and Y? My Y component is 1 meter, right? And so this is pretty good right here, right? 1.01, let's go right here, 0.98. Now I could tell Capstone to give me more resolution in those values, but I think we're good. So at a height of 0.98 meters, that projectile should be at 2.41 meters, at a 2.41 meter range from where it was launched. Okay, and so now what I'm going to do is move this, and I got my scale on the floor. Let's set this right over here to 2.41. Let me wait for my pendulum bob. So that's exactly 2.41 meters. And now, the only problems that you may have, and I may have as well, is sometimes somebody will bump the table, and it won't tweak the vertical, but it'll tweak the horizontal a little bit. But I think we should be okay here. So 1 meter up, 2.41 meters out. The projectile should be right here.
And so, Galileo, if you're correct, and all of your physics is correct, what you're going to show is that physics works from a model that you produced.
That's correct. Yep. And so we're testing our model right now. So we've created it using the code. Now we're going to test it. Okay, so 2 clicks, just like I did before. 2.41 meters.
Yay!
Perfect, right?
Nice gong.
Yeah. And so if this was a ring, it might have been difficult to see, but if this was a ring, it would have gone right through the middle. It hit right in the center of this, right? And so if we want to, let's find a different position for it, right? We could scan down through the data, you know, where is it going to land? What's the range of the projectile? We can trace our data all the way down to the bottom here. And we can see that 3.13 meters in that X direction will be the range where it'll strike the floor. Right? It started at 1 meter and it'll land down at the floor, 1 meter vertically. So we could put our cup, we could put our bucket, our paint can, whatever you want, right? It's such an amazing tool now that we can have the ability to create those mathematical models and generate data from it to help students make these types of discoveries and do these types of practicals and practicums. I think it's great. So appreciate it. Yeah.
Terrific.
Thank you.
You did it.
Yeah. Oh, and I did want to say one other thing. This projectile is nice and smooth. It has a very low drag coefficient. What you can also do is, this is a squishy Nerf ball, right? And so these fit in our projectile launcher, and they have a different coefficient of drag compared to these projectiles. And so if you wanted, you could go into the code and set a new drag coefficient. I'll just make it 2 for example purposes, right? And then you run this code again, and you can see how air drag affects the projectile path. And so you could load a different projectile in there that has a different coefficient of drag, and still figure out exactly where to put the rings or the gong if it was something a little more firm. So it's an amazing tool. Thanks.
Hey, no, that's awesome. JJ, thank you.
Thank you.
Thank you very much for showing that. And ladies and gentlemen, if you saw the great way that that demonstration took place here and you're thinking, I can't do this in my classroom, but I'd like to have this in my classroom, well, you can, because we can bring it to you every week, and all you got to do is check out our PASCO Academy, where we're putting these together for you so that in your situation, where you might be doing hybrid or distance learning, we can do this for you, even if you don't have the equipment. But maybe you want the equipment, and you should have it. Then just reach out to Isaac Martin, and remember our promo code this week. P stands for momentum. And you let Isaac know that you're ready to take a look at getting this projectile launch or any of the things that we're doing here, and he's ready to do that for you. So I just want you guys to know, as Ann is setting up, and I always want to call her Charles Sumner Miller, because when you see her demonstration, it's got that same Charles Sumner Miller approach to it. It's awesome stuff that Ann's going to do here. But do note we're live. And so what I would like to see is some of you out there trying to stump Ann, or have questions for JJ, or have questions for Jonathan, and let's get those questions in. And we can get them answered, we can address them for you, or we could even possibly stump them right here on the air. So, Ann, you ready?
I'm ready.
All right.
I don't need this computer.
That's so amazing.
So since JJ was doing projectile motion, I wanted to have another projectile demonstration. And as usual, things never work out quite right when you're trying to do demonstrations. So I've changed it to a momentum demonstration, but still using the projectile launcher. This projectile launcher, I've got what we call our drop shoot accessory here. It's got a magnet right here that holds on to a ball. And I've got the projectile launcher horizontal, and what you're supposed to show with this is that it's the old drop shoot that when one ball drops straight down, at the same time you shoot one out horizontally, and it has to be horizontal, that they have the same time of flight to the floor. So you're supposed to hear both balls hit the ground at the same time. Well, that's the tricky part here. You're probably not going to be able to hear that clicking in this situation. So I decided to show you a different aspect of this. Let me just cock this back. So I put one steel ball in the gun, and then, excuse me, I'm not supposed to call it a gun. I just, launcher. Yes, launcher.
Gotta be politically correct.
I teach college, you don't have to be that politically correct. But so, and then I've got an identical ball hanging out here. And conservation of momentum tells us that when one ball hits the other straight on, since they have the same mass, the ball that's hanging out here is going to gain the momentum that the other ball had. The other ball is going to stop short and just drop straight down. So it's a tricky way of getting a drop shoot mechanism. Let's try it out. Okay. And I don't think you could hear that, but they did hit the ground at the same time. Thank you. Now, the nice thing about this set is that it comes with different balls. And although these look identical, they're not. The one ball is hollow, so it's much lighter. And if you try to find these balls on our website, you have to look under the ridiculous name we gave them, which is the spherical mass set. It's not called the ball set.
Are we not allowed to say that either, Ann?
Apparently not.
I know we're not allowed to say that in middle school.
Yeah.
In college, you probably could. Spheres. Spheres.
Spheres.
Projectiles. Spheres.
So I'm just going to redo this, exactly the same thing. I put the heavy ball in the launcher, but now I have a lighter ball out here. So if momentum is conserved, the heavier ball is not going to transfer all of its momentum to that ball. And so this ball will go forward, but so will the other ball. So we'll get two balls going out, both shooting off horizontally. And the question is, do they hit the ground at the same time? If you can listen, you might hear them. Here goes. I can't tell. So now I'm going to, I need that table. Thank you. Yeah. And I need the balls back.
Spheres.
Oh, yes, spheres.
I have some spheres for you.
So the other part of this, which has nothing to do with projectile motion at all, is that these have different rotational inertias. Because one is hollow, it's got a much bigger rotational inertia because the mass is on the outside, and this one has the mass closer in, so it's easier to spin this one. So I'm going to put the balls together up here on the track. And I put one ball in front of the other and let it go. Hey, where's my foam? There was supposed to be foam on the end of this.
I got it.
Sorry, Ann. Foam's here.
Well, see, we actually sell this nice foam that damps things out.
All right, JJ. We'll see you again soon.
I have to stop and say that we really do have an excellent physics group here at PASCO. We all get along. So,
Most days.
yeah. So notice that when I did this, both the balls rolled down together. But now I'm going to do it again. And one gets ahead of the other. And the trick of that is that I started out with the hollow ball in front. The hollow ball is harder to accelerate, and it holds the other ball back. But when you put the solid ball in front, it easily accelerates, and the hollow one lags behind. So just a quick rotational inertia demonstration. Thank you.
Awesome. Thank you, Ann. Another great demonstration, another wonderful opportunity to explore some of the concepts in physics, and another great way that you can see that these things can actually be brought into your classroom. If you'd like Ann to come into your classroom weekly, we can find a way to do it. Just check out that PASCO Academy, and I know Janet's putting that PASCO Academy link up there so you can get more information and we can send it out to you. Who do we have coming up next? What's our next great demonstration?
We have Intermission by Adam Forgang.
Ah, intermission. All right, but don't go anywhere because I think you're really going to enjoy this.
Thanks for joining us. What is your name?
Adam.
Adam.
Do you need the full name?
What is your full name?
Full name. Adam Forgang.
Excellent. What do you do at PASCO?
I am a computer engineer.
What does a computer engineer do?
I devise solutions for our main applications, PASCO Capstone and Spark View, and then I implement them by typing using C++ code.
Okay.
Or
Excellent.
JavaScript.
What is your favorite part of your job?
That's a good question. I mean, of course, the first thing that pops in my mind is working with all the people,
Excellent.
designing the new things.
I can relate to that.
And then completing it bug-free.
Is it ever bug-free?
I can hope so. We do our best. We do our best. There's a few things still out there that we have to find time to fix.
Does it seem like bugs always just grow organically in the software sometimes?
Yeah, kind of. It does kind of feel like that.
What is the best operating system of all time?
Best operating system of all time? That's a good question. John, I'm a Windows user. That's what I'm used to. I've also worked with Mac, iOS, Linux, my past. I'd say I'm most comfortable with Windows.
Well, what's the best operating system?
That's a good question.
You love them all equally.
I
noticed you didn't say Chrome.
Chrome. That's true. To be honest with you, I'm not that, I mean, I love the browser. The browser's pretty good.
Absolutely.
I just don't have as much experience with Chrome.
Okay, all right, fair enough. What Marvel character would you get rid of, Aquaman or Green Lantern?
Wait a second. You said Marvel character, but those are both DC characters.
Oh! He's a pro. I'm going to blame that one on the question writer.
All right.
I think I just got owned.
I'm just saying, I'm a Marvel guy.
Oh, you're
so
a Marvel
I don't really
guy.
care that much about... I will say that when I was growing up in the 70s, back when we had Super Friends.
I remember Super Friends.
Aquaman was the guy.
All right. Excellent.
Because I could swim. That was like one thing I could do. I couldn't fly, but I could swim.
Excellent. Okay. Is water wet?
I feel like this is a trick question. It feels wet to me.
What would you name your robot butler?
My robot butler? I'm going to have to go with Jarvis.
Okay, excellent. What is your favorite element on the periodic table?
I'm tempted to say silicon.
Okay, excellent. Thank you for joining us, Adam.
Thank you for giving me the opportunity.
Excellent. All right, who's our next victim?
It's nice to have you back with us, and I hope you're enjoying the people of PASCO as we continue taking a look at the people that work with us, the people that are putting these things together. Now, in our first couple of demonstrations, you were able to see some of the mechanics applications, but we thought we'd switch gears a little bit, if you'll pardon the pun, and move right into electricity. And with us, we have somebody who has not been on our PASCO Live before, but you've seen many times on many of our video sets, and also has been answering all your great questions that come in. And the backdrop of all of our PASCO Live is Mr. Brett Sackett. And of course, I'm hoping you guys out there have some questions for Brett. Make sure that they come in. Make sure you get an opportunity to stump Brett as he goes through these great things, as he's going to demonstrate Faraday's Law. Mr. Brett.
Well, thank you, JP. Oh, who doesn't love Maxwell's equations? I love Maxwell's equations. And so one of Maxwell's equations is Faraday's law of induction. And so I really wanted to demonstrate that today because as someone who majored in physics and always really enjoyed physics and all of my physics instructors, you know, Faraday's law of induction is it's a fascinating relationship between induced EMF and a changing magnetic field. And while you're in physics and you're doing all sorts of calculus problems to kind of work this every which way you can, it's for some students it's a difficult concept to grasp. And so they might have experienced something like dropping a magnet through a coil, so that they understand that, you know, there is some induced EMF, or they might have seen a compass needle deflect. And so they can, you know, there's some ways to visualize what's happening with an induced EMF. But what I wanted to show today was a different way of showing Faraday's law of induction using some larger coils and we'll all kind of explain this in a bit. Let me talk a little bit about Faraday's law of induction, just so we can all get kind of on the same page. What do we need to do?
Other side.
Other side.
It's rubbing against your jacket.
I'm sorry about that.
And while they're doing that, Brett, there's a comment that came in on our live forum. Ivan is saying, make sure you show him something that's going to keep him awake in the Philippines.
Oh,
So,
excellent.
Ivan
Well,
in the Philippines.
Faraday's law of induction is a great way to stay awake at night anywhere in the world. And so what Faraday's law of induction says, that if I have an electric field and I do a closed loop integral around that electric field, that's going to be equal to the the negative time rate of change, and that negative is very important. That's Lenz's law. The negative rate of change of the changing magnetic flux, which is the integral of B dot dA. So if I have an area where the magnetic flux is changing through that area, the time rate of change of that flux is going to be equal to the induced EMF, okay? And so that's what I'm going to show you a different way to demonstrate that. That I think is really cool. So what's going on here? Well, I have our 550 universal interface, and the 550 interface, what it does is it has a built-in signal generator, and I'm using that as my driving potential. And so I am going to be running current through this coil, and we know that a current through a wire generates a magnetic field, and so this wire is wound around many times, which gives us a stronger magnetic field. And so I'm going to have a large field here, and then I have a smaller coil. So this coil here has a much smaller diameter, and it actually has more turns. I think the turns here are 200. So this is a 200 turn coil. This is a 2000 turn coil with a smaller geometry. And connected to the coil is a voltage sensor. That's also connected to the 550 interface. And so what's nice about having the voltage sensor and the signal generator in a dedicated unit is they're all timed together nicely, and you don't have to worry about having separate power supplies and separate voltage sensors. They all just work in an integrated unit. And so what I'm going to do is I'm going to use this, what we call the detector coil, which is connected to the voltage sensor, and I'm going to be able to detect the induced EMF because I'm going to be driving this coil with a changing voltage, which is going to give us a changing magnetic field. So over in Capstone, I have my first tab has all my equations if I want to lecture to my students like that. The second tab has the 550 connected to Capstone, and I have an oscilloscope display. So this is a live scope display, and I will turn the 550 on. And then in the controls panel, what I can do is I can change the waveform. And in Capstone, you can have a DC, square, triangle, all kinds of stuff. So I'll just click this down here so you can kind of see these are the different waveforms that you can use in Capstone. We're going to do a triangle wave. And the reason I'm choosing a triangle wave for the demo is because, you know, as we've just talked about Faraday's law of induction, what we're saying is that the induced EMF is equal to the time derivative of what will be my driving field. And so what that tells us is that the induced EMF should be the time derivative of whatever I'm driving the larger coil with. So if I have slopes happening, then, you know, if I have a changing voltage of, you know, a certain slope, then my induced EMF will be the derivative of that function. So let's try this and see what we get. I'm going to keep this far away from the coil right now, and I'm going to start this up. And so you see right now, my coil is picking up something. So I'm going to focus on my driving field here. Here we go. So the green triangle wave you see is the changing voltage. This is being driven with a triangle wave, and so that is giving us a varying magnetic field inside that coil, and of course outside too, to a lesser degree. And so you can see over here in the controls, if I, there we go. You can see here I can change my frequency if I want to see more cycles. And this is also showing you that this is live. So I'm changing the frequency. You can change the amplitude as well. So here is my detector coil, and I'm going to take this over here. And you see as I get close, what'd you see? Oh, look at that. Look at that. So notice that the induced EMF is what we would call a square wave. And I'm gonna let me select both of these so you can see them both. There we go. We've got some stray fields in here. Here we go. Look at that. Look at that. Oh, it's moments like this where I just love physics so much. So you can see that as I get this in here, I'm inducing an EMF, and that EMF is a square wave, because that square wave is the time derivative of the driving potential, which is a triangle wave. And then the great thing about this is that this is a hands-on way that students can explore Faraday's law. Yeah. So as I move this around, you can see I can look at different parts of this field. So I'm holding this outside, and you can see it's a square wave. The amplitude's not as big because the field's not as big here. And if I move this inside, you see that amplitude grow, and you can kind of move it around. Now, what would happen if I took my detector coil and flipped it around? Well, as I go perpendicular, it goes down to 0, and as I flip it around, you see it reverses, right? Because again, the induced EMF is due to the changing magnetic field, and this is where you'd want to talk about the right-hand rule and say, well, the current's going in this direction, so I've got a which I think the current's going in this direction. So if I right-hand rule that, I'll know which way the magnetic field is going, and then I can kind of conceptualize how's the magnetic flux changing through the detector coil, and you can move this around and see which is going to, determine a positive potential versus a negative potential. Another thing we can do is if I take this inductor wand, which is 2,000 turns, and swap it out for an inductor wand that is less turns, what would we expect to happen? And so as students are studying coils, they learn that there's a relationship between the number of turns and how that affects the EMF that can be induced in that coil. And you see here clearly this is a lot lower EMF because it has fewer turns, right? Excellent. So here's another way we can apply this is, I'm going to stop this here, and I'm going to go to another popular physics demonstration, which is the ring launcher. And so the ring launcher gives us a way to talk about some Faraday's law and also Lenz's law. And so I've got some rings here, and this, again, I've got a coil, and it's driving a much higher current. And then I have an iron core, because another thing we learn in physics is about how cores, or in this case, iron cores, can intensify the magnetic field. And so when I hit this button, this is just a momentary switch here, it's going to pulse the magnetic field right here. And so one way we can visualize that is this is a light bulb, which on the back here, there's a coil. And so I can see, right now, if I move this around this iron core, not much is happening. But if there is a changing magnetic flux, a changing magnetic field through this coil, we should be able to get an induced EMF. Let's see if we get that. And sure enough, so we're getting an induced EMF, which is lighting the light bulb. That's awesome. But as I'm doing this, I can feel the magnetic force. So there's a magnetic force happening here, and in physics, we love forces. So if I have a solid ring, this is made of aluminum, and I lay that there, what will happen is the magnetic flux through the aluminum produces eddy currents. Lenz's law kicks in and says, hey, let's go the other way. And what will happen is you get an induced EMF that launches this ring into the air. Wow, that's awesome. Let's try that again. I'm going to put this on, and nothing happened. Because this ring, if you can see that, does not make a complete circuit. So this ring is cut, so we just fooled the students. What about a smaller ring? Like that. Not as high, because we don't get as big of a repulsive force. And this is copper. What will happen with the copper? Well, one thing I know is that, wow, this copper is a lot heavier. So it doesn't go quite as high as the aluminum. And so that, my friends, yes?
John Wilson has written in and said this appears to him to be a nice way to talk about step-up and step-down transformers. What do you think?
Yes. Yes, I think you could definitely do that. Absolutely. So that's all I had for Faraday's Law. Thanks for joining. I think we're going to have another interview with another person at PASCO.
Awesome. See you after the intermission.
Thanks for joining us.
Thank you.
Can you please introduce yourself?
Sure. My name is Mike. I'm a member of the teacher support team here at PASCO Scientific. I've been here since 2008.
All right. What is the best part about your job? What do you enjoy the most?
I love the fact that when I'm on chat or the telephone rings, I could be talking to anybody from a kindergarten teacher and student all the way up to an engineering professor. So it keeps me on the top of my game.
So you have to know a wide range of products.
Certainly.
Okay. What's one of the more common tech support calls that you get?
Trying to do particular tasks within the software. So how do I rescale my graph, or how do I display this type of data on my graph within the software?
Okay, so lots of calls, they call in, and you're one of the tech support people they can talk to, and there's other people back there as well, right?
Yeah, I'm just a member of the three folks that work in our department.
Okay. Do you have a funny tech support call or story you can tell?
Well, we have lots of people that are interested in growing all kinds of different plants.
Okay. So,
that sometimes is a little bit funny.
And so you're fielding a lot of those kinds of calls.
Yes, it can be anywhere from algae to any variety of plants, as well as trying to characterize, like Tibetan prayer bowls in terms of like getting their sound characteristics.
Okay.
There's a wide variety of things.
Excellent. And you're the guy for the job.
It's a lot of fun. Yeah,
Okay.
It's a lot of fun.
Excellent. Now, for that special someone in your life, for your wife, if you could get your wife an anniversary present, and it's anything in the PASCO catalog, what would you get her? Sky's the limit.
Goodness. The Ecozone.
Ecozone. Okay, excellent. That I like that answer because she could use that for growing any kind of plants.
Exactly.
Okay, excellent. Okay, we're going to go into the lightning round here.
Okay.
Okay, you ready? So, who would win in a rap battle? Isaac Newton, Albert Einstein?
Isaac Newton.
Best NFL team, Raiders or Cowboys?
Niners, of course.
Marvel, DC?
Marvel, of course.
Star Trek, Doctor Who?
Which Doctor Who? Tom Baker.
I love this guy. He knows his Doctor Who. Excellent. I agree, totally. Mike, thanks for joining us.
It's been fun. Thank you so much.
See some more of the people here at PASCO, and I want to say a very special thank you to Marie, who has complimented our group here, and you're absolutely right, Marie. We have a great group, and that's why our products are so good. And a special shout out to Leonardo, who I know well and has been a friend of PASCO for many years, and thank you for the compliment, Leonardo. It's certainly appreciated. We have a lot of great demonstrations. Now, you just saw some good stuff on electricity, but what you kind of want to get into now is maybe talking a little bit about light and waves and diffraction, and we have an opportunity to do that. And of course, we're going to show you how we can do that here, and we're also going to show you how you can get this product if you'd like. Remember our promo code, P stands for momentum, and you just let Isaac know that you would like this opportunity to get in on this promo for any of the things that you see here, or if you'd like for us to do this for you in your classroom every single week, then just check out PASCO Academy, because we're putting together a great program so that you can do this type of distance education, working with your students from home, working with your students in the classroom, working with your students when we do the demonstrations for you. We discuss the labs for you, we collect the data for you, we give the data to your students, and then your students can do the analysis and share it back with you. And so that's what we're here for. We're here to do the physics, we're here to show you how we can do it, we're also here to bring you some great products. And thank you all for joining us. Coming up now, we have somebody who's been joining us on many of our shows in the past, and he's got over 30 years in education, 30 years of working with students, and 30 years of trying to get this experiment to work here as we're live, and we're putting in some filler, is Mr. Dan Burns. Ladies and gentlemen, Dan Burns.
Thanks for stretching that out, JP. So I have PASCO's wireless diffraction scanner here, and it allows you to do one of the things I really think works well with students is to have them use the physics they've learned to make a prediction about something. So it's a theoretical exercise, but then do the experiment and compare the two, a lot like JJ's projectile experiment. And the diffraction scanner gives data so good that you can check some predictions as far as what the light intensity pattern is for a double slit or a single slit, or actually when you do double slit you get both overlaying. So let's take a look at what the data looks like and then compare it to a model that I've already prepared. And so we hit record, and I have light intensity on the vertical axis. Oh, I know, all these stage lights. We better zero the sensor first. That'll work a little better. This does work really well in a brightly lit classroom, but doing it on in a studio is challenging, but I think we're going to get some good data here. So you can see the main pattern and then off to the side. And so there are equations that predict what that pattern should look like based on the number of slits, the slit separation, the slit width, how far apart the diffraction grating is from the screen, and the wavelength of the laser. And so I have put all those in and did it for this same slit and laser, and also have it with theory. And so, there we go. And so this shows a previously collected set of data that's exactly what I just did there, different color though. And there's a text window that I put in there. This could be used to help students, and it tells them how to set up their model. And over here in the calculator window, so instead of Blockly, we also have a very robust calculator for putting in closed form solutions. And you can see I've put in the theoretical double, well, it's kind of tiny print there. If you're watching on your phone, you won't see it. But students would be able to see it there, and I can even read it. And so once I measure the data, I would measure the intensity of the maximum peak, so I know what the max intensity is. And then I'd measure its position so I can shift things a little bit. And then I also put in the slit width, slit separation, and how far apart they are. And so the two are this, the green is the measured, and the orange is the theoretical. And so that's a beautiful match between data and theory of a pretty complex phenomena. Now the other thing the scanner comes with is this set of slits. And so it's on a wheel, and you can turn it and change the slit separation, the slit width, the number of slits. There's single, double, multiple, and then some sort of fun ones with dots and holes and squares and stuff. And so let's take a quick look at the difference between a double slit and a single slit. And I can go back the other way. I don't have to go positive here. So if I hit record, I can just turn the wheel back the other way. And you want to kind of go slow, but not really slow. It's compared to taking these measurements manually, this is highly efficient. There's a position sensor in here that is also measuring where the screen is in the sensor. And probably should have zeroed it again, but you get a nice single slit pattern as well. And so you can get the whole set with all these things together, but some people already have our lasers and our diffraction slits, so you can just buy this by itself. And so this is a new, and it's wireless, which really helps. And so the new wireless diffraction scanner, one of my favorite things to work with here at PASCO. It's a long list.
Awesome. Thank you very much, Dan. Ladies and gentlemen, Mr. Dan Burns. So Dan's got 30 years of education, and he's going to be putting in another year of education. If you want him to be bringing these things into your classroom, you can do that. Just check us out on PASCO Academy. And I know that Janet's going to put that PASCO Academy link there so that you can go in and take a look. Who's coming up next, Nolan?
Tina.
Tina.
For intermission.
Ah, okay. We've got an intermission. You get to meet another fine folks here at PASCO, meet our people, and we'll be right back.
Yeah. Thanks for joining us. Can you please introduce yourself?
Hi, my name's Tina Wood.
And what do you do at PASCO?
I am a new product introduction specialist. I help with the new products when they come out. I'm a lead in the assembly area and help training and work with the engineering on some of the new projects for the new boards, prototype boards.
Right. So when we do a prototype board, you're sometimes in there putting some of that together.
Yes.
And that's sometimes a lot of very small components.
Very tiny work, yeah.
So you're kind of like a wizard when it comes to that.
I'm getting better at it.
What do you enjoy most about your job here at PASCO?
Besides the people I work with are great. Variety of work has always been fun. There's always something new every day to work on.
And how does working at PASCO compare to assembling guitar amplifiers at Mesa Boogie?
Oh my goodness, this is much more fun. That was like the same things every day. You built an amplifier, sometimes different variations of it, but yeah, this is a lot more fun.
Right, okay. For that special someone in your life, if you could buy them anything from the PASCO catalog, what would it be?
The arm. The human arm.
The human arm model?
Yeah.
Okay, yeah. Excellent, excellent. Who would win a rap battle? Sir Isaac Newton or Albert Einstein?
Einstein.
Okay, I'll go with that. That's excellent. Thanks for joining us.
Okay, you're welcome.
Good? Good. One take. Thank you for joining us.
Of course.
Can you please introduce yourself?
My name is Janet Gomez.
What do you do here at PASCO?
I do social media. I also do our digital content. And I'm also a graphic designer.
Awesome. And what do you enjoy most about working at PASCO?
Working with Boomer, being able to just come up to people and take their photos so they usually run away from me. That's pretty cool.
Right. How difficult is it working with Boomer?
You know, it's really easy to work with him. He's actually very cooperative. He could be a brat, though, but...
Is water wet?
No. Like, I had to think about that.
Who is the best NFL team, Raiders or the Cowboys?
Niners! No question.
What would you name your robot butler?
Alfred.
And what is your favorite element on the periodic table?
Iron.
Who makes the best tacos?
Chondos.
Yes. Who's your favorite boss?
You? I know I nailed that one.
All right, that'll show up on your review.
Thanks.
And again, that was great to see some of the great people working here at PASCO. And I just kind of want you to know that this isn't our standard set. We're actually working in a part of PASCO right now where a lot of our inventions are kind of like produced and thought about. It's a great place. Anne is here. You see some people. Brett, take a look around and show the folks at home kind of like where we're working. We see all the great things here. This is just a great laboratory where things are developed and your ideas are brought to life. And we certainly enjoy the opportunity to bring your ideas to life, and we're thankful for the great things that you folks are saying out there. Hello to Brenda Martin, who says she misses us, and certainly for all of our educators. We certainly hope that you're all healthy and happy out there, and we certainly miss you guys too. And Lori, a very nice compliment on the systems that you've been seeing here. Thank you, Lori. A very nice compliment and a special shout out to you, with a special thanks to all of our folks with all this great stuff. Now, it looks to me like we're going to be doing something with Star Wars, and are we doing something with lightsabers, or what's the deal here?
Yeah, that's our rotational inertia wands, which was a very old demonstration, and we made it new. I'm going to have JJ help me with this. These two wands they appear to be identical except for color. They're not. And I'll show you. Here, JJ. Now, I want you to do this as quick as you can. Come on.
I'm trying.
You're stronger than I am. Of course, I gave him the hard one.
I am really sure on that.
So just to show you, these two are hanging from a pulley. So if one of them was heavier than the other, it would go towards the side that was heavier. But they're not. They're the same mass. So it's not that he's just weak and can't lift it.
Well, maybe a little bit. Maybe he is after all. Yeah, maybe he is, but...
So I wanted a way to show you what we're feeling. And what I'm feeling is this. I've got this on a wire so that there's a restoring torque. And so when it's fairly easy to do this one. And then poor JJ, I gave him this one, which is much harder to rotate. So the wire can't make it rotate as fast as it makes this one rotate. Now, if you examine these closely, you can actually see the difference because there's a hole right here on the red one, because there are two masses in here and they're close to the handle. And then this one has exactly the same masses, but instead of being close to the handle here, they're out on the end so that is actually filled up on the slot here. So the rotational inertia of the blue one is a lot more just because of the mass distribution. It's got the mass further out, just like the hollow ball in the last demo had the mass further out. And this one has the mass further in, and of course is easier then to rotate. So that's the rotational wands. Now, we need to exchange tables.
All right, let's move this table out.
Watch out.
Let's knock that light down.
Ouch! Just kidding.
Let's bring our next table in. And ladies and gentlemen, just so you know, and just so that everybody knows, Anne Hanks is celebrating 30 years with PASCO this year. So a very nice round of applause to Anne Hanks, who's celebrating 30 years. 30 years right here with PASCO Scientific. And of course, you can have her in your classroom. If you just want her, just let us know. She can join you on the PASCO Academy. What do you got for us, Anne?
I need the computer on here. So this is a neat demonstration for oscillations. Two carts. These are smart carts. Let me turn them on so I can record their position and velocity. And I've got to connect to the carts. So there's always a pause before the great demo. And, you know, we have a lot of carts and tracks, and the diffraction apparatus is apparently still on because I'm seeing it show up here when I go to connect to my carts. But the carts show up at the top of the list when I'm trying to connect because they're closer to me than all the rest of the stuff in the room that has a radio on. Did not connect to that one. There we go. All right. So in a system like this, it happens to have equal mass springs, the equal spring constants, but you could change that if you like and have them be different spring constants. But this oscillates it has two resonant frequencies. This is one of them, and that's a fairly slow frequency. And then this is the other one, which is a higher frequency. So it has two different modes. And we can show this on an FFT. I'm taking an FFT of the velocities of the carts. Let me record here. And I'm just going to give this a little hit, just kind of randomly. And you'll see on the FFT, I just hit it randomly, so there's a combination of the two different modes. And you can see on the FFT here that I'm getting two different peaks. One is if I go and force it into this mode, then you'll see that that mode is the one that is building now, and the other one is decreasing in time. So that's that frequency. Now I can force it into the other frequency. And now that peak is going to build. So you can see that it's pretty neat that you can get both frequencies just by randomly throwing the carts, so that they're not doing either motion exactly. They're kind of jerking around. And it's a superposition of states, but it works. It's great.
Physics rocks.
Yeah. Okay, so who's next? That's JJ.
Thank you, Ann. And thank you for that demonstration, and thank you for bringing both the smart cards, the track, and the software to life right here for PASCO. And Ann, you've been here with PASCO for 30 years, but how long have you been married? How many years have you been married?
44.
44 years. And is your husband here with PASCO also?
Yes, he is.
He's hiding.
Could he come over and say hello? Come, bring him over. As JJ's coming, I think you guys need to see the working team of Hanks and Hanks. Married 44 years, working for PASCO forever. Many of the great products you see, many of the things that you've seen today, including the Smart Cart, Brain Children, and Inventions, and produced by the Hanks and Hanks team. So thank you both very much. It's nice to have you with us, and congratulations, Ann, for 30 years. Awesome stuff. All right, JJ,
Yes.
you have not been here for 30 years.
I've been here for 16.
16 years, and 16 years means that you can show us some really great stuff. What are you going to show us?
I need the mic. And you can kind of hear me.
Sorry.
No problem.
Can you hear me now?
I can hear you, but I'm standing right next to you. I hope the folks
Okay.
at home can hear you. Yes?
We good? All right. So what you may have seen me doing just now is I've got a little piece of paper towel here, and I'm running it up and down the track. And you might be wondering why I'm doing that. So I noticed in Ann's demo, when her carts, they were smart carts, when they were rolling back and forth, I heard a little tit-tit, 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 tit-tit as they were going back and forth. And what happens is there's two grooves in this track, a wide one and a narrow one, and they're intended to receive the wheels of all of our dynamics carts, whether it be the pass car, the smart cart, the go car. We have tons of different carts. Stuff can fall down in there really easily, and oftentimes the wheels will pick it up and then redeposit it down there. And so if you're worried about friction or data being, absolutely perfect, no bumps, no, issues with your velocity data, I'll take a paper towel and I'll fold it up real tight and I just run it down the lengths of these grooves, and you can clearly see sometimes that there's a lot of buildup that'll end up in there. So now when you roll the carts, nice and smooth, no bumpy noises. So what I want to show everybody is it's basically a demonstration that involves energy. Okay, and so I've got this cart, this dynamics cart. Its mass is about 250 grams. Okay, and then I've got this friction block. It's nothing spectacular. It's great because it's got several surfaces that we can put down on our track here, and it will produce a frictional force, and we can put it in front of this cart here, and if I push this, that frictional force works from outside the system, right? So we've got this block and cart system, and then there's friction between the track and the block that's, working from outside that system. And so we can explore how energy is converted, what happens to it, and make predictions about what we suspect in terms of the motion of this system. And so what I'm going to do is there's a plunger on these carts, right? And so I'm going to compress this plunger, press it up against this end stop, and then put the friction block in front of it, okay? And now there's a little trigger here. I'm going to launch it, and this cart is going to push that block down the track. And eventually it comes to a stop, right? There's a frictional force that's doing work, right, to stop that block and cart as they move together. Okay, and remember I said the cart is about 250 grams. So what happens? Yes, let me grab that. So this will help us mark things in a second. What will happen if I double the mass of the cart? So I have these bar masses here, 250 grams each. I've got a few of them. What happens if I double the mass of this cart? So I'm just going to put that in there and redo our experiment. All right, so we're gonna go to our students and we're gonna ask for a prediction. What's gonna happen? Okay, and I get a lot of different responses. Students will oftentimes say, "Oh, it's heavier. It's gonna go. We've doubled the mass. It's gonna go half as far, right?"
Oh, but you doubled the mass, so it has more inertia, right?
Yeah, so it's got more inertia, right? So it's gonna be harder to get it going, right? So let's see what happens. I'm gonna press that plunger in the same amount. And I'm going to set it up again. Oh, I forgot. We should mark the position just to help us, right? So I'll just do this again. And you can see here, I'll put that right about there to tell us that the front of that, actually, maybe I'll move it back just a little bit. The front of that block stopped here. Okay, so now double the mass, compress the plunger the same, set it up, and then launch it again. And look at that. It travels the exact same distance. But why? Why does it travel the exact same distance? And now let's make a second prediction. Let's say I triple the mass. Okay, so I'm going to triple the mass of the cart. What's going to happen again? Now students might have a little bit of an inkling as to, well, maybe it'll go the same. Because we doubled it and it didn't change. So maybe it'll travel the same distance. So let's compress it again. Same amount of compression of the plunger, right? And I'll use this to help me launch it. And although it took a little bit longer for it to get there, it went the same distance again, right? So what's happening? Well, the answer is energy, right? And conservation of energy. So whether the cart has 250 grams of mass, 500 or 750, the energy that our system started with was all from this plunger, okay? And I emphasized it a second ago. I compressed the plunger the same every time there's actually a spring inside these carts, whether it be the smart cart, the pass car. There is a spring, and when I press this plunger in, it compresses that spring, some amount, right? Now, we don't care about the absolute amount that it gets compressed. We just know that now our system, when it starts over here, it actually starts with energy. And as this system moved horizontally along this track, its potential energy didn't change. Its gravitational potential energy didn't change. But its kinetic energy definitely did. It sped up and then it slowed down. So where did that energy come from? It came from spring potential energy inside that cart. We compressed the spring. The system now has energy to start with, spring potential energy. We convert that spring potential energy to kinetic energy, right? And then all of that energy leaves the system as work is done by friction. Same amount every time because the system always starts with the same amount of energy. We compress the spring the same. So it doesn't matter if it's 250, 500, 750 grams, or even higher, right? The system, no matter what its mass is, starts with the same amount of energy. And that energy gets converted, right, to kinetic energy. And like I said, that last example, the cart was moving slower, right? So it had the same amount of kinetic energy, but a much lower speed because its mass was so much higher. And all of that energy gets sapped out, right, as friction does work. I shouldn't say sapped. It gets converted into heat energy, right, as friction does work on the system to slow it down. So it's a great example of a semi-low tech.
Don't put it away.
Oh, okay. I'll leave that there.
No, I want to change the mass.
Oh, yes. Yes, you do. But we've changed the mass of the cart, so now you want to change the mass of...
I'm going to set the mass here.
Ah.
Yeah.
Okay, now let's see what happens.
That's why she's got 30 years, JJ.
That's why she's the queen of physics.
That's why we celebrate Anne Hanks.
Okay, so now Anne has changed the mass, right, changed the amount of mass that's sitting on top of this block rather than putting the mass in the cart. Okay, and so now what I'm going to do is launch this, and look at that. It didn't go nearly as far. And so what's going on here? Well, we've effectively changed the amount of frictional force acting on the system as it moves forward, right? So it starts with the same amount of kinetic energy, but friction is doing a much larger magnitude of a job. Yeah.
By friction.
Yes. And so, yes, so we have the same amount of kinetic energy to start with, but now that gets converted to heat energy in a much shorter distance. And we can add even more mass if we wanted to. And it gets shorter and shorter. So, yes.
Awesome demonstration, JJ, and thank you for that. And again, thank you for the people who keep reaching out. Carol had a very nice hello to us. But Carol, you got to let me know what country you're coming from, because es verdad, very entertaining. Sí, gracias for your compliment, and para mí tan demasiado. Sí? But thank you, JJ, and thank you for all of our folks. And who's coming up next here? What do we have to show our folks next?
I think let's do an intermission. Are we doing it? I'll have to refill one. Oh. I think we'll be fine.
Okay, looks like we're going to a brief intermission, and then we'll...
I think we're just going to roll it in and go.
Ah, okay. We have our next demonstration coming in. Who's doing this? Is Brett doing this? Yeah, this is the great thing about live television. Brett's going to be doing our next demonstration, and it looks like we're working with...
I can do this. Okay. This.
Electricity.
You want to do this one? Sure. Okay.
Somebody will be doing a demonstration, and we'll be doing that demonstration live. Gentlemen?
All right, so last time I was here, I talked about Faraday's law and what happens when we have an induced EMF due to a changing magnetic field. Well, check this out. This, I'm sure many of you recognize the Genicon, right? And this is connected to a coil. This coil here has a lot of turns on it, I think like 4,000 or something. And then here I have a magnet suspended by one of our track dynamic strings, and if you're
springs. And if you're a physics teacher, you should always have some of these springs because they're useful for so many different things. If you've ever gone shopping for springs and you're at Home Depot, you know none of those springs work for a physics class. So we find springs that are handy for physics demos. So what I'm going to do is I'm going to get this magnet stable there. It's suspended right above this coil. And now, if we only had a changing magnetic field, which we can get by producing giving us a potential difference across this coil, that will produce our magnetic field. But we want it to oscillate. So you know that when I have a Genicon and I turn the crank, right, I get a DC voltage. But if I want AC, all I got to do is move it back and forth, and that's going to get me a varying voltage. And so, notice when I turn it that way, it pulled the magnet down. Let me start that again. And so what I'll do, I'll go the other way, and you see it hops it up a little bit, right? I'll do that again. I'm going to go up, right? Now I'm going to go down, right? So now what I need to do, if I want to have a alternating magnetic field, is I'm just going to take the Genicon and kind of work it back and forth. And you can see I can quickly get to a resonance frequency because I get a pretty strong alternating magnetic field. And it's, again, it's the time varying magnetic field that is the magic to Faraday's law. And don't forget that negative sign in front. That's Lenz's law, also key to understanding the full Faraday's law of induction. Are you ready, JJ?
Yeah.
I'm going to go mask on and off camera.
So let me turn this around and get it pointed at that camera. And I just want to make sure that what you guys are seeing is what I want you to see. So give me perfect. Okay. So what we've got here is it's a giant concave mirror. Okay, and in front of this concave mirror is just a little foam basketball. Purple on top, orange on the bottom. And the focal point, the focal length, right, of this mirror is right here. All right? And so this ball is hanging right at that focal point. And so what's going to happen with it hanging there, we see this giant blown up, right, virtual image of the ball. Let me take this off. Virtual image of the ball in the mirror, right? We see this blown up image. So what happens if I give this ball a little pull and let it swing back and forth through the focal point, in between the mirror and the focal point, and outside the focal point? Okay, and what I want you guys to notice and pay attention to is the ball has purple on top and orange on the bottom. All right, so here we go. I'm going to get it going and get out of the way. All right? Yeah. So what's happening to the image that we see? We still see that virtual image, you know, in the mirror, but as this ball travels through that focal point towards the mirror and out past the focal point this way, the image flips, right? We get this inversion of that virtual image. And so that's how you know when you're looking at these concave mirrors whether or not you're within that focal distance or outside of it, right? Because if you've ever been to like what are those house of mirrors? And you look, in the fun house and you get real close to it, you see a giant magnified image of yourself, right? But you're upright, you're in between that focal point and the mirror itself. If you're back and you're upside down, you're outside that focal distance. So, very easy demo to set up.
Cool.
And thank you, JJ, and thank you for that demonstration, and thank you for all of you who are watching us. If I'm understanding correctly, it looks like we're at the end of our demonstrations for today. Am I correct on that?
No, there's more.
Awesome.
There's more. There's more.
There's
We
more.
do have more?
Oh, wait, there's more.
But wait, there's
Oh my
more.
goodness, today is the bonus round. We have more demonstrations. What do we have? And who's doing it? And I have absolutely no idea. The beautiful part of who's doing it?
But Jonathan?
Jonathan is going to do for us
Optics.
optics. Excellent. Okay. We have a great opportunity to do some optics, so let's get this stuff out of here. And let's bring this stuff in here. And Jonathan, how many years do you have with PASCO?
Oh, I have about a little over 6 now.
A little over 6 years, and excellent. And so you probably don't see Jonathan too often, but you know a lot of the stuff that he writes, because many of the labs that you get, many of the manuals that you've received, many of the product information that you get, all comes from Jonathan. So he's an excellent writer, awesome physics teacher, and can be in your classroom also. Just ask for him as we put together our PASCO Academy. And Jonathan, we are ready for you.
Okay. Okay, so let's see here.
And mask off.
Oh yeah, mask off would be good. Let's see. Oh, guess you can't hear me, can you? Not necessarily a bad thing, but.
Jonathan, you're awesome. We love you.
All right. Can you hear me now? Okay, so let's see. So do we have a good view of the screen? Okay. All right, so this is a pretty cool demonstration. So what do we have here? We have a light source that has 3 different colors in here. We have red lights, and we have a green light. Looking good? Okay. And we also have a blue light. So what we're going to look at here is what happens when we mix those colors together. So let's just start with the red. And let's take a look at the green. Ooh. Isn't that beautiful? I love visual stuff, which is why. I know. Yeah. See, I used to do this with floodlights, and it's not as impressive with floodlights. So yeah, when we have green and red together, we get a nice color of yellow. And you notice too that as we adjust the brightness, it changes from a yellow to more of an orange. So this helps explain how we get all the different colors, say like in a television screen or a computer monitor. All right, let's try red and blue. So what do we get out of that? Oh, we get a lovely shade of what? What do we call that color?
Magenta.
Magenta, excellent, good. We got the right one. Yes. Okay, so good. So we got blue and red gives us magenta. Let's try one more. Let's see. So we did red and blue, and then let's try blue and green. So let's see, what do we get here? Another kind of shade of blue, but it's not blue. What is it, JP?
Cyan.
Cyan, excellent, Brad. Wonderful, yeah.
Cyan.
Yeah. So, okay, and then let's do all 3 together. Why not, right? So we put all 3 together, and we get a great shade of white. Well, actually, it kind of looks pinkish white on my side, but it's white enough. Yeah. So this is this shows us how we get all those different kind of colors that we have in our screens. And but let's take it one step further. What about shadows? So if we just have one color of light, and let me bring in, can you see that okay on the?
Yeah. Yep.
All right, excellent. So we got a shadow, black shadow. I mean, nothing spectacular there. Let's bring in the green light. Okay, so now yellow. Let's bring it in there. Hey.
Wow.
What do we got there?
That is interesting.
Yeah, not only do we have 2 shadows, but we have 2 shadows of 2 different colors. And boy, my hand is shaking like crazy here. Yeah, so why do we have 2 shadows now? We got 2 different light sources, right? Now, which light source is causing the green shadow? The red light or the green light?
Red.
then I'm going to go with green.
Yes, the red light is causing the green shadow. So basically what's going on there is that when I take this out, okay, you notice that take the green light out, the shadow is just black, and then when we bring the green light in, it fills in that shadow with green light. Let's try a different.
Cool.
I know, it's awesome, isn't it? Well, let's make a prediction first. Well, how many shadows are we going to get first of all?
Two.
Two, right. What color should those shadows be?
Blue and red.
Yeah, blue and red, right? Okay. And let's try a last one. Let's see. With cyan. And actually, let me come up on the other side. That might work a little bit better. Is my hand in the way? No? Okay. Come on, there we are. All right. Yep, and again, two shadows, green and blue. All right. Now let's go crazy. Ooh. Ooh, yeah, I know. Yeah, please, don't stop me here. Okay. Yeah, 3 lights. Okay. What do we predict now? How many shadows, first of all?
3.
3 shadows. Okay. What colors will those shadows be? Any cyan?
Red, green, and blue.
So I hear red, I hear green, I hear blue, I heard cyan. Magenta. Well, let's see. Let's see, got a good angle there. Oh, look at that. They're not red, blue, and green. Instead, they are magenta, cyan, and yellow. Why?
Tricky. Very tricky.
Yeah, so what's going on in that case? Well, okay, here, right now, we have blue and green shadows. So when I turn on the red light, okay, the red is going to mix with that green, gives us yellow, and the red mixes with the blue, gives us magenta.
Jonathan.
Isn't that awesome?
Jonathan.
Physics is awesome.
Yes, it is.
Anne would have loved that when she was little.
Yeah.
And if they would have had electricity back then, she would have done it to work.
Oh, man. Okay.
I have to say that I have asked many physicists, and they did the same thing I did as a child. They arranged your crayons in the order of the rainbow by wavelength. I did that.
All right, so let's take this another step further. I have these special cards here. They're cards that transmit different colors of light. So you can see there's green, blue, red, and yellow. So let's see, and also let's take a look on here. So I'm not sure how well you can see that. If you can zoom in on that. Each one of these cards also has a graph on it that shows what colors that these filters transmit. So obviously a blue filter is going to transmit blue very well. Let's take a look at another one. Yeah, green. Yeah, it's mostly in the green, of course. Not perfect, but pretty close. Yeah, mostly red for the red filter. Now, what about the yellow filter? So, what color would yellow transmit best? Obviously yellow, right? But what else?
Blue and green.
Oh, actually, close. We got red and green, actually. Yeah, red and green make up yellow. So, let's test that out on here. So, blue. If I put the blue. You can see that it transmits the blue. What about red? In this case, nothing gets through. Yeah, there's no red in there, right? And then, of course, with the green, as we would expect as well, yeah, none of that green light gets through the blue filter. And of course, you would see the same thing. Like if I put red here, no light gets through because it's a red filter. But if I do turn on the red light, of course, the light does get through. Now the yellow, okay. Yeah, we don't have any yellow light here, but we do have red and green. So, yep, yellow filter allows red light to get through. Allows green light to get through. And you notice it is green and not yellow. And then blue as we would predict, no light should get through. And indeed, no light does get through. Actually, if you can look a bit of light gets through, and actually if you look at the card actually does show a little bit of blue light can get through, but it's really hard to tell, and this is good enough for physics, right, for teaching physics. Okay, now,
Nicely done.
Thank you. But wait, there's more. We also have cards that reflect light as opposed to transmitting light. And you'll notice here I got also, we don't have magenta, but we have pink. I'm not sure exactly why, but I guess it wasn't in the budget. Let's see, we got red card, and we have also 2 different types of yellow cards. I'm not going to do all these cards.
Is this soccer?
Soccer? Yeah. I'm sorry, I don't know sports. So we actually have a whole bunch of other different color cards too that I don't have with me today, but I'm only going to show a couple of these. So red naturally is going to reflect red, and you can see on here, the red has a pretty huge bump on there. So if I put this, put the red in here, yeah, you can see the red, and you can see the color very well reflecting off. But what if I change it to green? It's not reflecting as well anymore. It's quite a bit darker, isn't it? Actually, are the overhead? Yeah. If I get some of the overhead lights, like that light right over there, is actually. It's looking pretty black. Okay, excellent. Nice. Ooh, wow, that looks so much better on the camera.
We all do, Jonathan. We all do.
All right, and then let's see. Yeah, the red and the blue. I don't know, how's that looking? Looking pretty. Yeah. Excellent. Yeah. Okay, now let's try yellow. I love the yellow. Now, as I said, I got 2 different types of yellow. Okay. So I'm just going to stick with the plain yellow to start off with. So yellow, we know what 2 colors make up yellow. We saw red and green, right? So it should be reflecting off of those pretty well. So I turn on the red. Yeah, it reflects pretty well. It's not looking too dark, is it? Gosh, that looks so great on the camera. Wow. I am impressed. That is awesome. Okay, let's take a look at green now. Yeah, looking pretty good. Okay, now let's try blue. And as we can see, it is quite dark, isn't it? It's absorbing a lot of that light. It's not reflecting it at all. Okay, now let's try the fluorescent yellow, which let's see if I can get this. Okay, if you can see, they look similar. I mean, you can probably see that there's a little bit of a difference to the fluorescent yellow. I'm not sure if you can see with the cards. Let's see if we can try to zoom in on that. Okay, yeah. You'll notice that the profile on the graph is very similar. The fluorescent yellow has it's a little bit higher up in the orangish and red area, but overall it's pretty much the same. So let's see how it looks under each of these different colors of light again. Again, start with red. Yeah, reflects off pretty well. It's reflecting the green pretty well. Okay. And the blue. Oh my. It's not absorbing the light as much.
Great.
Yeah. So, and actually, it's not reflecting the light either. And this was actually confusing me earlier. I had to ask Ann about this. Because the profile said pretty much the same thing. So, what it's actually doing, it's absorbing the blue light and re-emitting it.
In the yellow.
In the yellow, yeah. Okay. One more demonstration with light that's related. So we're going to look at a different type of filter now. Yeah, let's get these out. These things are awesome. So we got polarization filters. I don't know. Well, I don't need the lights on. No, I actually have a light myself here. Let's try this guy. Okay. There you go. And if you could zoom in on that as well, just to take a look. The equipment looks better than me, so yeah, make sure. Okay, all right, there we go. Can we see that okay? Yeah, okay. I think we should be all right here. Okay. Now, ooh, that looks pretty. I like that. Okay, so you'll notice, okay, I have these two polarization filters here, and similar to those other filters, sorry. Oh yeah, you can see me. Okay, you can see well enough. Yeah. So these polarization filters, instead of filtering out color, they filter out light in a specific direction. And I put markers on here so you could see this a little bit better. So this actually filters light in this direction. If I rotate it by 90 degrees, it filters it in the horizontal direction. So I'm going to put that in here. And I'm going to put this one at the same angle, so you should be seeing light getting through. Excellent. Now I'm going to go ahead and rotate the one in front. And unfortunately, you can't really see the tabs. You can just see it a little bit. It looks like it's right somewhere around there. Oh, there's a delay. That's making things really tough. Okay, so as I rotate it, though, now we're filtering out all the light. So because this first filter is filtering out light only in the horizontal position, and the one in the back is filtering out in the vertical position. Okay, now let's take it one step further. I have a third polarizer. Oops, oh, you can, excellent, thank you. And this one actually does show the transmission axis on it as well. So if I put it in this way, yeah, light doesn't get through. If I put it in horizontally, yeah, light doesn't get through. But what if I put it in at an angle so there is a vertical and a horizontal component? Ooh. That gets me every time. I just love that. Yeah, so yeah, by putting it in at an angle, yeah, we have a horizontal and a vertical component, so it's allowing, basically kind of half of that light to get through. Now let's use something else as a filter to go in between. Now this is getting into chemistry, so I'm not going to even begin to try to explain how this works. You're going to have to wait for a day of chemistry on this one. But apparently some substances can polarize light as well. In here we have, I don't know, is it caro syrup or corn syrup? Yeah, okay. Corn syrup, okay. Now I'm going to go ahead and put that in here. Isn't that just amazing? I tell you, it's so surreal. I mean, it's just, I'm getting there. I'm trying to get the dramatic effect here. I'm trying to appreciate this beautiful moment in physics. Now, let's rotate it. Now, first of all, what color do we see?
Jonathan's favorite color.
Yes, yellow. Actually, green's my favorite, but yeah, we see yellow. Okay, so let's rotate it and see what happens as we rotate it. We should be getting another color there, right? Yeah. It's kind of hard for me to see from my angle, but we're getting cyan there, I think. And as we turn, yeah, there's that cyan should be looking pretty good. Yeah, keep turning it. Is magenta appearing now, hopefully? Magenta's coming in, nice. Yeah, isn't that beautiful? So those three colors, those three colors are familiar, aren't they? We saw that with the color mixing. So what's going on in this case? Well, I don't know exactly everything that's going on in this case, but I mean, I guess one thing that I did notice is that every 30 degrees, or no, sorry, not every 30, every 60 degrees, we're getting a different color there. So it appears that, yeah, at different angles, we're only one color is getting filtered. So like in this case, if we go back to the yellow, okay, there we go, yeah. Going to the yellow, so in this case, we have red and green getting through, but not blue. So blue is getting polarized. All right, let's try one more thing, and then you can get rid of me. This is for Mike Paskowitz, who you saw earlier in an interview. He's our engineering guru here at PASCO. Okay. All right, so this is from our materials testing system. And if you could see that, yeah, so this is one of our beams from our structure set. It's not a typical beam. This one's a clear beam. It's, I'm not sure, what's the type of material this is? Is this what, polycarbonate or?
No, I think it's acrylic.
Acrylic? Okay. So that has interesting properties when you put it in here as well. Let me try, can I make that a little darker? Oh, isn't that pretty? Now, the cool thing about this is that you can see the stress in the beams when you actually place a force on it, place a load on it. So hopefully this shows up in the camera, but I'm going to use my screwdriver to apply a force. I don't know, can you see that stress on the beam?
Jonathan, look at that. That is beautiful.
Pretty amazing, isn't it?
Yes.
Physics is awesome.
Yes, it is.
All right, thank you very much.
Thank you, Jonathan.
Thank you, Jonathan. And finally, I'm able to say that my degree, my PhD is in chemistry, so I can tell you it's because those molecules are chiral, and we will be talking more about chemistry and looking at optical rotation. And finally, they just let me host these shows, but it's really nice to be able to actually talk a little bit about my knowledge. And thank you, everybody. So are there any more surprises hidden in this dark room?
Yes. Yes.
We do have more surprises?
Yes.
Okay. What do we have coming up?
Pressure demo.
Okay, let's take a look at being under pressure. Let's get some lights on if we can. Let's bring JJ back and let's take a look at pressure.
Oh yeah, sure.
Well, JJ's coming back. Do you remember that our questions, you can ask questions at any point, and we've got a lot of great questions coming in. I'm glad we're able to answer them. This is recorded. If you want to go back and watch this, if you have another 3 hours that you want to watch physics demonstrations, you're welcome to do so. This will be on our PASCO Live channel. Just take a look and find it there. You'll find all of our PASCO Live opportunities there on our PASCO Live channel, pasco.com. And if you'd like to bring any of these demos to your classroom, you're able to do that just by bringing the PASCO Academy into your classroom. We're going to do a full semester 1, full semester 2. When you need it, we're here for you. We're putting it together, doing exactly what we're doing here, but we'll be doing it for you as teachers, we'll be doing it for your students, giving them the data, giving them the opportunity to explore, and giving you the opportunity to teach through distance learning using our equipment and our staff. All right, JJ, under pressure, you ready?
Yes, I am not quite ready. Give me, okay. I am ready enough. Okay. So, I've got some demos that I want to show everybody with regard to pressure. More specifically, atmospheric pressure, right? We may not realize it, but around us every day, all day, well, most of us, I should say, there's air, right? And air is made up of gas molecules, right? We've got hydrogen, nitrogen, carbon dioxide, oxygen, there's all kinds of stuff in the air. And those molecules have mass, right? I mean, they just like the molecules that make up me as a person, this is a table, these handles, they have mass, right? And that mass is what's responsible for the air pressure we experience that we may not realize is happening. And the weight of all that gas is pushing down on us. And so air pressure changes as you go up in altitude because there's just not quite as much air pushing down on you as there is when you're down here where we are in Roseville, California. And so pushing down on us at any time under normal circumstances is about 15 pounds of force per square inch of surface area, right? And so this is what I like to tell everybody to do. If you make an OK sign, the area of that OK sign is about 1 square inch, right? And so in every OK sign, there's 15 pounds of force pushing on you. So if you go like this, that one little spot on your arm is 15 pounds pushing. 15 pounds, 15 more, 15 more, 15 more, 15 more, 15 more. And so the total amount of force pushing on you is pretty substantial when you add it all up. Now, why don't we feel it Well, it's because of several circumstances, but most importantly, air is pushing on us from all directions, right? It's below us, it's down by my feet, it's above us, it's above my head, it's on either side of me. And so if I hold my hand out here, how come I don't feel force pushing from the air on my hand? Well, it's because that force is canceled out, right, by the same equivalent magnitude force in the opposite direction, right? So we don't feel it. And it's easy to move my hand around in the air because those two forces cancel out. So what happens if we have the ability to take away all the force from one side? Well, this is kind of how pressure works. If you have force pushing on one side from air pressure and force pushing on the other side from air pressure, you get zero net force. If you take away pressure on one side, now you have a net force in a specific direction. And so if all of a sudden there was no air pressure here, that force would push my hand that way because there is a substantial total amount of force there. And that's what this device helps us demonstrate. This is PASCO's atmospheric pressure demonstrator, and it is nothing more than a smooth piece of plastic, rubber I should say, floppy rubber, with a handle on it. And the handle is aluminum. It's it's not magnetic. It doesn't stick to anything metal, right? There's no magnet there. But what we can do with this piece of rubber is we can put it down on flat surfaces just like that. And what we've done is we've taken the air that was just a second ago underneath it here and remove it. It pushes all the air out from underneath it. And now there's only air applying a force on the top of this. Okay, and what you'll see is, and students love this demo, it's impossible to pick this thing up off the table.
Don't believe
you. Right? I mean, the substantial amount of force pushing down from air pressure is holding it to this table. It's now I have to deal with the mass of this table, right? If the weight of this table is now part of what I'm pulling up here.
So what lifted the table?
So the force that I'm applying lifted the table plus the force of the air pushing from underneath, right? So, but just to show that it's not a trick, this isn't sticky, okay? There's no gooey stuff on here, right? And you'll hear a lot of people say there's no such thing as a force of suction, right? It's actually you're removing that force from the other side.
Nothing sucks in physics.
That's right, that's right. So, and so that force is pushing down and it makes it impossible to lift this thing up. Now, if I put this on this stool here, okay, watch this. It comes up, no problem, right? So what's different? Well, you may not have noticed, but on my stool are small holes. And those holes actually allow that air pressure to push, right? And in fact, when I pull up on it, this piece of rubber, air slides in underneath it, and that air pressure helps me push it up, pull this up off the chair. Okay. And so this is also a fun demo. These are what are called Magdeburg plates, right? And this is just a rubber O-ring. And what I have on top of this plate is a small access hole where I can connect a pump, basically. And so if I take this and I put this on top of that O-ring, it seats, right? But I can lift this thing up. And the reason is there's air underneath. There's air in that gap between this tabletop and the bottom of this plate. So it comes up no problem. But what happens if I remove that air? I remove that air pressure. So I'm going to hook this little pump up, and I'm just going to pump the air out. So I've taken the air out from between the bottom of this plate and the top of this table. And now you can't get it off the table, right? And I mean, and it's really on there. And so if I let the air back in, I heard a little hiss, you may not have heard it. It comes right off, right? So air pressure helps us everywhere. Now, I'm going to demonstrate in a little bit more dramatic fashion. Well, I think it's more dramatic. So this is a balloon, just a standard rubber balloon. And what I've done is I've put just a tiny bit of air in there. and I've tied a knot on the end. So I've trapped that air in there. No air can get in, no air can get out. But you'll notice that the balloon is real soft. It's not expanded. There's no tension in the surface of this balloon. That's because the pressure of the air inside, the force from that pressure is equal to that outside. So the air pressure inside is equal to the air pressure outside, right? It's easy to move the surface of this around. And just to show you that no air can get in or out, if I squeeze it, right, that air is trapped in there. So I'll put this balloon in this little chamber here, and basically what this is the demo that I just did with this on top of the table, but in a taller vessel, a taller airspace here. And so I'm going to take my pump and I'm going to evacuate the air out of here. So what do we think is going to happen? So right now the air pressure inside the balloon is the same as the air pressure outside, right? So the balloon shape stays static. It doesn't change. So now, if we take the air pressure from outside around surrounding the balloon, there'll be no more force pushing onto the surface of the balloon. There will be only force pushing from within the balloon. And so let's see what happens. Did you guys see that? So what's happening to the balloon? The balloon is actually expanding. Without that force from outside, that atmospheric pressure from outside surrounding the balloon, pushing down, the force from inside is free to expand the surface of the balloon. And if we had a bigger chamber, that balloon would probably keep growing until that tension force from the surface stopped it from expanding. Or it popped, yeah. So if I let the air back in, what should we see? Well, now we're going to equilibrate the pressures inside and outside the balloon. Boom, and it goes right back to where it was. Still the same balloon, nothing different. So let's go one step further. Who likes marshmallows?
Who doesn't like marshmallows?
Okay. So, who knows how marshmallows are made? Actually, I'm kind of lying a little bit. I don't know exactly how they're made. But marshmallows are, it's a puffed sugar solution, right? So you have this sugary concoction that's like a slurry. It's real liquidy, but viscous. And then they foam it, they bubble it with air, right? And what happens is a bunch of air bubbles get trapped in there. And it makes these marshmallows nice and squishy. And so this is an air bubble. Now we've got trapped air bubbles in here. What do you guys think is going to happen when I put the marshmallow into the chamber? Okay, and so before I put our friend Marty the Marshmallow in there, I'm going to turn him around, and then I'm going to shut the lid. Oops. And now we're going to see what happens to our marshmallow as I remove that atmospheric air around it, leaving only the air trapped in the little bubbles that are inside the marshmallow. So what's going to happen? Well, we saw the balloon expand. Will the little bubbles in the marshmallow expand? Let's see. Marty's putting on some LBs. Nice. Okay. All right. And you might not be able to tell, but the marshmallow is actually starting to shrink a little bit. Okay, and Anne had a great suggestion earlier with the balloon. If we took enough air out of it and the tension wasn't strong enough, the balloon would eventually pop. So we can assume the same thing's happening here. Eventually, those little air bubbles in the marshmallow start to pop, right? And now I'm removing even more of that air out of there. Because as they pop, I'm now pumping that newly popped and released air out of there, and the marshmallow starts to shrink a little bit. So what's going to happen to the marshmallow when I let the air back in there? Okay, so on the count of three, one, two, three, go. All right, ready? 1, 2, 3, go. Oh. And so what I like, yeah, what I like to do is I like to tell students that this is actually a time machine, right? So they start small, they grow up, and then when you let the air back in, they get really old really quick. And that's what happened to Marty. Okay.
Right on.
I don't know. I don't want to go there. Okay, so now I want to talk to you guys about magnetic braking, right? Magnetic forces. Brett was talking to you about forces. In fact, he mentioned eddy currents just a minute ago. Okay, and I want to show you a demonstration involving eddy currents. And to do that, I'm going to use this magnetic forces demonstration set, right? And this is our variable gap permanent magnet. Amazing magnet. The strength of these magnets is absolutely insane. Okay, and so let me take these off of here. Before I put that up there, let me just demonstrate the apparatus. So these little spatula looking things, they hook onto this arm and they swing, right? Back and forth. And so there's 3 types of spatulas. There's a solid one, there's this one with holes, and this one with veins, right? And so these veins are actually open at the bottom, and this spatula, the veins are closed. All right, and so what I'm going to do is put this permanent magnet up here, and I'm going to align these veins so they swing through this magnet, through the poles of the magnet. Can you guys see that okay? So this spatula, actually before I do that, let me go ahead and put this flat spatula up there. Okay, so I'm going to let go of this flat spatula, and it normally just swings freely back and forth. Okay, but now I'm going to have it swing freely through this magnet, this really strong magnet. What's going to happen? Okay, we've got a conducting material here, aluminum. We've got a very strong magnetic field that goes this direction, right, towards the camera. What's going to happen? So well, let's find out. Ready? 1, 2, 3. Air brakes, right? So nothing forcefully stopped that was touching it, right? So there was nothing touching the spatula, and it stopped. Right? We'll do that again. And it just stops. Air brakes, right? So what's going on? Well, let's try this spatula now. This one has veins on it that are open at the bottom. Okay, so I can actually hook both of these up at the same time and make sure they don't smack into the magnet. And I'm going to let go of both of them at the same time. Okay, what's going to happen? So why did that one go through, but the solid one didn't? It stopped. And the answer is eddy currents, right? So as this flat spatula travels through the magnetic field, right, it starts moving electrons. And you get this new magnetic field produced from the movement of the electrons on the surface of this metal. Okay? And that new magnetic field is intended to oppose the one that's going through there. Right? And in doing so, you get this force that stops that spatula. And so this eddy current drives the electrons in a circle, right? And as they drive in a circle, just like a coil of wire, you get another magnetic field that's produced, and those fields oppose each other, and there's forces that stop it. Okay, so why did this one swing right through? Well, if you paid close attention to how I described the direction of the electron movement, it goes around in a circle just like this, right? But what happens if electrons go around in a circle on this one? Well, they can't, because they run into air, right? They can't jump this gap between the veins on this spatula, so you don't get the same eddy currents that you do in this one. And I mean, you might get small ones that get induced here and here, but the magnitude is nowhere near what you get with this one. So now the third spatula is where you bring it all together. So now you still have holes in the spatula. The electrons can't jump this gap, but they are connected at the bottom, so now you can produce a closed loop for those electrons to move around in a circle, right? And so what happens with this spatula? It also stops, right? We drop it, it swings through, and it also stops. But it doesn't stop quite as dramatically as the solid spatula because the electron path is constricted based on the geometry of the spatula, but it stops. And so if you swing both the open-ended and the closed-ended vanes, only one of them swings through freely, right? Those are magnetic forces. And then the last thing I want to show you is a Lenz's law demonstration that everyone loves, including me, right? And what we've got here, oh, can I use that stool you're sitting on?
Yeah.
Thank you. What we've got here is an aluminum pipe. It's nothing fancy, it's just an aluminum pipe. Where's that no bounce pad? It's perfect for this. Do you see it? So what I'm gonna do in this demonstration is this aluminum pipe, I've got, we'll call it a slug, but basically it's a battery wrapped in masking tape. Oh, thank you, Ann. Right, it's a battery wrapped in masking tape, and if I drop this battery through here, let's see if we can count how long it takes to hit the pad. Ready? On the count of 3, I'm going to drop it. I'll go 1, 2, 3, drop. 1, 2, 3, drop. It's about a second, right? Flies right through. Okay, and if this wasn't there, and I dropped it from about the same height, it would take about the same amount of time. So its path wasn't impeded by this. Its motion wasn't impeded by this aluminum pipe. Now I've got a stack of magnets, very strong neodymium magnets. Okay, let's count how long it takes these magnets to go through. 1, 2, 3, drop.
1, 2, 3, 4, 5, 6.
5 times as long. Okay, and what's happening here, the same thing that we saw here, we are dropping this magnet in there, and that magnetic field is inducing current flow in this pipe, in this direction, right? And as current goes in that direction, we get a B field that opposes this incoming B field, right? Lenz's law, we want to keep that flux the same. It doesn't, these metals don't like it when you change the magnetic field that goes through them, right? They try to create their own magnetic field to oppose that. And that's what's happening with this. So that magnetic field drops through this aluminum. The aluminum produces a magnetic field that pushes back because it makes those electrons go around the pipe in that circular motion. And so that's magnetic forces. Thank you very much.
And okay, and thank you, JJ, and thank you for that. And tell me, Brett, are we at the end, or is there another surprise?
That's everything.
We're actually at the end. And ladies and gentlemen, I hope you really enjoyed everything that you saw here today. Best thing I could say is don't try this at home, but let us do it for you. And you can do that with our own PASCO Academy. And if you'd like to try this at home, all the equipment that you see here today, Isaac Martin is ready to give you that FOMO promo. Reach out to Isaac and let him know that P stands for momentum. He's going to give you a great discount on everything you've seen here today. So a round of applause for all of our folks that put on some great demonstrations today. And a round of applause for any of you who managed to stay up for 3 hours watching. Congratulations to you. You all get a PASCO certificate. And to everybody, thank you so much. We wish you the best of luck, great teaching, and good day.